Hey Omar, can you hear me? Right.
Hey, John.
Hey, can everybody that's on already on here also hear us? I guess so.
Yeah, the chat should be available.
Yep, and they're all confirming they can hear us. All right. Have you tweeted this YouTube live link yet?
Yeah, the YouTube live link is up.
Yep, and they're all confirming they can hear us. There's that 15-second delay. That's great. 5 are watching on there. We are not. Well, we're broadcasting some volume now. We just haven't been saying anything. Also, I think we're all on mute, so you can't hear us typing and other kinds of things. So it would have sounded really quiet. We'll get started in about 15 minutes. All right, we have 84 participants. We'll probably get started in a few minutes. Really from all over the world. It's really awesome. All right, I think we're probably about ready to get started. Omar, do you want to start recording?
Yep, the recording's live.
All right, so I guess we're told to tell everyone we're recording, so you know. We're going to try to post the recordings of all the talks somewhere, somehow after we're done, and we see what we get. So welcome everyone to the first @CAT virtual meeting. I'm super excited to have everyone here. It looks like already 137 people we've seen in the chat from all over the world. So we have a super exciting day ahead of us on this. Let me start by thanking Omar and Zach for putting together the program. This was originally part of the ACS program that got canceled, and it looked so exciting that I approached them to see if we could do this online. And Omar's really done a tremendous amount of work on the tech side of getting the webinar license, figuring out how to do everything. And Paul Downhauer, our first speaker, has really been fantastic in the marketing effort and kind of brainstorming how to do this. So the symposium today is called Beyond the Curve, Breaking Past Scaling Relations. And all of these talks are a variety of topics on how to get past the linear free energy relationships and their influence and impact on scaling relations and catalysis. So we have a really great program set up. We'll start out with Paul and then Zach. We'll have a half-hour break for lunch or coffee or tea, or depending on where you are and what time you're at. And then in the afternoon, Omar will talk, and Hong Leong and Charlie Sykes. And then we'll have another break, and then we'll have 3 more talks after that. At 3 p.m., we'll have a wrap-up discussion so that you can chat with us and think about brainstorming for future events that might be like this. So I want to just give the speakers a little reminder about how we're going to do it. You have a time slot that's listed here. We will give you a little bell sound that might sound something like this when you have like 2 minutes left. And when we would like you to leave some time for questions. And so if you run out of time, then we will do something that sounds like this. Oscar style, just, speak over that until you stop. So hopefully everybody will keep us on schedule so that our slides here don't get too out of date. And the audience, you're all muted, and there should be a Q&A box that you can ask questions in. And there will be a poll available either now or soon. If you could please answer that to help us with planning events, that would be helpful. And I'm going to paste a link here in the chat to all of you. That is to an interactive or editable Google Doc that we can have going on throughout the day, where you can put comments or questions or anything like that. So with that, I think we can probably make, let's see, Omar, do you want to say anything else?
No, John, that all sounds great. Yeah, thank you all for being here. And the poll that John was just mentioning has gone live. So please take advantage of that to let us know how we can make this better for the future, what you liked, what you didn't like about that. And if you have a comment that doesn't quite fit into the pre-configured questions, feel absolutely free to shoot any of us an email, and we'll definitely work on those comments.
All right, so Paul, I see you're already listed as a panelist. If you want to go ahead and share your screen, then we will get started with Paul Downhauer as our first speaker. So Paul is a professor of chemical engineering. If you're on Twitter, you know he's probably the most prolific tweeter in the catalysis community, and also is an entrepreneur and innovator in catalysis. And today he's going to tell us about the newest thing that he's been working on, which is an idea of dynamic catalysis, catalytic resonance, and a really exciting way to get past a lot of steady state limitations in catalysis. So with that, Paul, I'm going to hand it to you. And one more thing for the audience, what we'll do is have questions in the Q&A, and we will moderate those, and we'll feed those to the speaker when your time for answering questions is. All right, so how about Paul, take it away.
Okay, can you guys hear me okay? John, can you hear me? Okay, thank you for the opportunity. Thanks to the organizers and everything, and people for calling in. I'm going to talk today about this new concept that we've been working on which we're calling catalytic resonance theory. And this connects to a lot of the problems that we were aware of in looking for new ways to use catalysis to solve some of these sustainability challenges. And I'll give you one of them as an example. there's this issue that we have now low-cost wind and solar power, but we have it in places where we don't live. And for example, one way we could think about utilizing this is to put massive solar arrays in the middle of Australia, where there's a lot of dirt, sand, and scorpions and snakes, and then be able to convert that into hydrogen, which we could then convert into ammonia, put into tankers, and move around the country to places like India or China, Japan, that have very high energy density. Of course, the challenge there is implementing all of this in terms of renewable energy technology, but also the catalytic conversion of water to hydrogen and then hydrogen to ammonia. And these are classic problems in catalysis. If you think about these things conceptually, they all have a sequence of events that have to happen. The first step being adsorption, the second overall step is surface reaction, and the third step being desorption. And it's been known for a long time that these types of systems and a lot of catalytic chemistries exhibit these Sabatier volcanoes that you see on the right, where the turnover frequency of the reaction is a function of some descriptor of the reaction. In this case, I'm showing it as the relative binding energy of B star, the surface product, where as I go stronger in binding, the desorption rate becomes limiting and the rate goes down. As I go weaker in binding, I become reaction controlled by the surface reaction. And when I actually balance this out, I reach this optimum for a static material, and beating that maximum has been the challenge. Now, if I think about how we can overcome this problem, I could think about how I could try to balance out all the steps to get the best possible scenario, but I'm always essentially cheating one step to benefit the other. And so this has been the kind of the premise of modern catalysis. A search for materials. We have this belief that we can take a reaction like we see on the right, where the uncatalyzed system has a very high barrier, and think about finding a material that drops us down to some catalyzed mechanism where the transition state energy is lower to go from A star to B star. Of course, the problem then is your desorption energy is so high that we have to balance that with the energy associated with the surface reaction. And so what we're looking for is a way to both reduce the binding energy, but also at the very exact same time, reduce the transition state energy. And so I say this here is broken in blue, because what we've done is we might have the same surface thermodynamics, but the transition state energy is lower. So we've changed the scaling relation between that. And of course, the question is, will we find a new material, be it a nanoparticle or a MOF or a zeolite or a single atom, that can give you a different scaling relation that tries to make the catalyst energy pathway as flat as possible to get from A to B? And that's the question. Will we find that kind of magic material that's able to break all of these, or appeal to every single individual elementary step? And so what I want to propose is an alternative. Rather than trying to find one material that can meet all of the demands of all the steps at the same time, let's take a dynamic material and make it such that it changes with time, such that when each event in the elementary sequence happens, that catalyst changes for that particular elementary step. So let me start with a very simple case here, this A to B reaction. In the first case, state one, it's favorable to go from A to A star through the transition state to B star. And then when we oscillate to state two, now it's more favorable for desorption. And so when we think about flipping between these two states, we can think of it as favorable for each of the two rate limitations of surface reaction and desorption. And when we do that, if we come back to this idea of Sabatier optimum, we're thinking about this now as two sides of the volcano, but in this case, we take each of the elementary steps and we extend them up above the Sabatier optimum. And if we do this flipping of states at the right frequency, we'll eventually overcome that optimum and try to achieve this tie line between the two dashed lines you see up there on the very top. Now, the question is, how do we do this experimentally? How does this behave in terms of a real system? How does it behave in terms of a theoretical system? All of these things are big picture questions that we'd like to tackle. And so to do this, we've put together a team of people working on this all together. This is all funded through the Catalysis Center for Energy Innovation, U.S. Department of Energy program. And you can see my picture there is on the left, but we were combining together all sorts of concepts of theory, computation, experimental synthesis, and experimental reaction dynamics to try to understand these particular systems. Now, I'm going to talk all about the theory behind this, but two talks after me is going to be a talk by Professor Omar Abdelrahman, where he's actually going to show you an experimental system where he's been able to implement some of these ideas and show proof of concept. So his talk's at 12:30 Eastern time today. And he's going to actually show you this figure right here, which looks like the conceptual figure I showed you a few minutes ago, where you can actually see the static conditions here, the electrostatic conditions, give you this optimum. but the dynamic conditions at 100 hertz go over an order of magnitude faster than what you could achieve under static conditions. You'll have to see his talk to kind of get all the details on that particular system, but I want to give it as a teaser here and to let you kind of think about, in my talk, what are the conceptual issues that show up, and we'll get to how we implement this later. So let's explore this computationally. Let's take a theoretical system. We'll stick, just for the time being, it's complicated enough to think about a conceptual reaction if A goes to B. And we'll include all the elementary steps in between, and these could be equilibrated, they could not be equilibrated. We allow for all of these possibilities. And you think about just the parameters we now have. We have the normal reactor parameters of space, velocity, temperature, and pressure. We have all the parameters that show up in the catalytic chemistry, such as the thermodynamics, heat of absorption, transition state energy. But now we've doubled the number of parameters because we have to account for the dynamics, the amplitude of the dynamics, the position of that amplitude oscillation, the frequency that we do that, and of course the waveform type and shape that the oscillation takes. So let's take a simple scenario here. So I'm taking now a system that flips an energy from strong to weak binding of the surface species B star. And you can see it up on the top left. It goes from strong binding to weak binding with an oscillation of 0.6 electron volts. And what you see is as you flip from strong to weak binding, the product B, the instantaneous turnover frequency there in the middle, shoots up very quickly and then comes back down as you leave the surface. You can even see that on the bottom set of data there, where I'm flipping the surface coverage between species A and species B. So essentially, we're oscillating between a surface covered in A and a surface covered in B. And every time we flip, we push some amount of material off that surface. And the instantaneous reaction rate goes up very high. Now, when you average that reaction rate out, you'll get something that's significantly higher than you could get under static conditions. And you can think about then, well, how fast should I flip between the states? And so the data you're seeing here on the left is this instantaneous turnover frequency to the product B. How is that being formed with time? And I'm showing this now for 4 different frequencies. The simulation starts out at one fixed static condition, and then you can see where all the colors emerge in the data. Those are 4 different frequencies. So at very low frequencies, 0.001 hertz, the system actually just rapidly comes to a steady state that's very similar to a static system. It's actually quite slow. As you increase to 0.25 hertz, now the dynamic system matches the static optimum. And actually, as you go above that, 10 hertz, you're almost an order of magnitude above. And at 1,000 hertz, you can see several things that are interesting. It takes many oscillations to come to a new dynamic steady state, but also that the oscillation here reduces as well. Now, if you put all this together, if I take each of those different frequencies and say, what's the average turnover frequency, and plot that as a function of the applied surface frequency, I can now look at this in terms of the plot you see here on the right, where the bottom is the applied frequency to the surface, and the vertical axis is that averaged reaction rate. And what you see is that my static optimum there in red is about 0.25 to 0.3 turnovers per second. And as I increase the applied frequency, I eventually get to this linear region where I increase in rate and stop at about 30 turnovers per second. And this is this resonance frequency where I've actually matched the applied dynamics to the natural dynamics of the reaction. And that goes all the way up to about 1 megahertz, at which point I can no longer fill the surface fast enough and the rate drops down. And I lose the benefit of matching the applied dynamics of natural dynamics of the reaction. Now, of course, that's just for a given amplitude, right? I've been using 0.6 electron volts, and it's for a specific range of application. But I can think about fixing where I apply the amplitude, but also then change the width of it and the frequency at the same time and look at the turnover frequency. So the plot you're seeing here on the left, everything I've been showing up to now has been, if you look at the x-axis on the bottom there, has been at 0.6 electron volts. So if you go up that vertically, starting from the very bottom, and then go vertically up, you can actually see where that resonance band exists. And you can see you get up to around 10 turnovers per second, but around 1,000 to a million hertz. And what you see, though, is that as I make small increases from 0.6 to 0.7 to 0.8 electron volts in amplitude, the rate goes up significantly to the point where if you were able to achieve something as large, which is quite large, as a 1 electron volt dynamics for this particular system, you would in theory, you get 1,000 turnovers per second, which is something like enzyme levels. And you'd be at the range where you couldn't actually achieve these turnover frequencies because you hit a new diffusion limitation. Okay, so what can change in these systems? You think about that's kind of a computational exploration of one particular system. But we think of all the possible chemistries that are out there. We have to think about how the chemistries actually differ. And one way they're going to differ is in their reaction scaling parameters. And you can see here, if I think about this BEP relationship, the two surface species, A star and B star, we can think of them as a change in energy. Their transition state's also going to change. In this case, we're describing it by this linear relationship with parameters alpha and beta. And so if you go back to the volcano plots that we talked about earlier, you can actually see on the left there, these volcano plots as we change this alpha scaling parameter. And at a high alpha, we have this steep slope with a very tight volcano. And as we make that smaller and smaller, it becomes flatter and flatter. Now, of course, this matters for the dynamics that you apply. We think about the amplitude of how we're moving from the left side to the right side of the volcano. Of course, the volcano shape itself matters for what rates we can achieve. Now, if I go forward here, this is a steep volcano. This is an alpha of 1. And what I've plotted here now is the turnover frequency on the vertical axis on the left panel, and as a function of the relative binding energy of B, just like we've been talking about. And if you think about applying different amplitudes, what you're doing in the purple points, the tie lines above the volcano peak, is connecting two different independent elementary steps, depending on, and the height of which depends on the applied amplitude. You can see now why small changes in the amplitude give you huge benefits in rate. And if all of these systems, if you look on the right panel now, you can see actually give you resonance frequency band, but those benefits differ, you can see in the bar plot inset, in terms of the average turnover frequency you get. So for a high alpha and a high amplitude, you would theoretically achieve impossible turnover frequencies over 10 to the 4 or 10 to the 5, which could never be achieved. So this is essentially an extreme case. Now, other chemistries, if we go from an alpha of 1, now I'm going to show you a system with an alpha of 0.4. Now what we've done is taken the volcano and broadened it out, such that amplitudes that previously were being able to achieve higher rates above the volcano can no longer push as far up because the tie line between them has to extend further out. And you can actually see that on the right side now. We still get this resonance band of frequencies, but now the bar plot only extends up to 100 to 1,000 turnovers per second at these extremely high amplitudes of over 1 electron volt, which of course is quite extreme in itself. But even in the low end or lower end of half an electron volt, which is very achievable experimentally, we're still getting reaction rates here on the order of 100 turnovers per second, which is incredibly high. Now, what else can we change? Well, so we can change the amplitude, the chemistry itself will change, but we can also think about the dynamics that we're applying. So rather than a square wave, I can think about other waveforms of the surface I can apply. In this case, if you look at panel A, I'm applying a sinusoidal wave where I'm going between strong and weak binding. This is the exact same amplitude and system I was talking about earlier. Now we've only changed the shape. And what you see is if you look at the panel B, you still see this as we flip from strong to weak binding, we see this spike in the turnover frequency as we empty the surface. The shape is a little bit different, but so is the shape of the surface coverage in panel C, where you see I'm going between a mostly filled surface of A to a mostly filled surface of B, but it doesn't completely fill or unfill in this particular case. And so the question is, what's the difference in effectiveness of these different waveform shapes, keeping all the parameters the same? And so if I go to the next set of data, you can actually see this right here. I'm comparing square waves to sinusoidal waves to trigonal and sawtooth. And what you see is that in every condition, basically the square wave is as good or better than every single performance of every other waveform we look at. And this makes conceptual sense. If we're trying to make the reaction surface chase the preferred state, trying to achieve a new steady state every time we switch, we would like to always spend time at the extremes to make it chase between filling and unfilling surfaces with favorable and unfavorable transition states. And anytime we spend in between these two oscillation states, really that we're not driving the reaction in any favorable direction. That's why the square wave, which is always instantaneously flipping between favorable states, is going to be the most effective by a little bit. Now, what else matters? Of course, the scaling relations for the transition state are important, but we can also think about how things move on a surface. So trying to characterize all possible systems and thinking of this big picture, we have to think about all the possible scenarios. And luckily, there aren't that many new parameters we have to worry about. We still have the overall heat of reaction, delta H of reaction. We have the parameters for the transition state there in the middle I was talking about. So the activation energy is a function of alpha and beta. But now we have to think about how the two intermediates, A star and B star, are also changing relative to one another. And so we need two new parameters in this case to think about how these are related. People have proposed these parameters before for other systems, so it's not entirely new. If I think about this, I want to think about how A star and B star are changing relative to each other by some amount. That's the slope. And then I need some fixed point in energy that I can relate between the two. And the point that seems most obvious is this point we call delta. You can actually see it in purple there on the left side. It's the point in energy where both A star and B star have the exact same value in energy. And that's important. I'll get to this later in the talk about why that point is actually special. But between those two now, I can put this plot up where I show the heat of absorption of A versus the heat of absorption of B. And I can think of these things. In this case, I'm going to plot them, assume they're all linear in this case. They don't have to be linear, but in this case, that's how we're going to describe it as a first pass. So here you can see the heat of reaction of A and heat of reaction of B, and they have this delta point of common energy. But then any possible accessible heat of absorption or binding energy changes along this line. In this case, my gamma, my slope, is greater than 1. So one of the species changes more than the other. In this case, it's B. Of course, that could be smaller. You could have different delta points. These things all depend on the surface, but also the adsorbate, but also the stimulating method you use to change the binding energy itself. So what are those methods and how do they really change? We can start thinking about this just by looking at something like periodic metals. In this case, I'm actually thinking about how different metals interact. So this has been known for a long time. This is data taken from Mavroukakis and co-workers, where they looked at the different ammonia intermediate species adsorbed on different surfaces. And what you see here is that the heat of adsorption of NH star versus NH2 star is linear across these different metals. And you can see there the gamma is 0.5, that's the slope. And on the right side, you can actually see NH star versus NH3 star has a much lower slope of 0.2. Now, of course, if I'm doing this dynamically, what I would like to do in this case is have something like ruthenium in and then quick switch that to gold. And if I could magically turn one element into another, that would be desirable. But of course, we haven't invented that technology yet, and we're not going to. So we need to think about other stimulating methods by which we could make a binding energy change with time. And a lot of other people have looked at this before us. This is work on the left side here from Jean-Sabine McEwen, where he looked at the adsorption energy under different electric fields. Where in this case, I'm showing the adsorption energy of formaldehyde, hydrogen, and methane as a function of the methanol binding energy. And you can see again here, these have different slopes, but also they can have negative slopes. So in this case, methanol versus formaldehyde move in opposite directions. Another way to think about this is something like surface strain. If I change the surface strain, I'm changing the binding energy. And you can see here that all the different species show up in, or different metals show up in different places, but they also have different slopes. And of course, to achieve these large binding energy shifts with strain is difficult to actually implement because you need incredibly large, likely infeasible levels of strain. So what else is out there that we could use to tune the binding energy? There's, of course, electrocatalysis, where we know that the charge counter layer forms, this double layer in the liquid with a local electric field, which we know electric fields can tune the binding energy. But we also have this variation of the surface potential. For something like a Faradaic reaction with an electron energy, that can change quite dramatically. And I recommend you stay on if you're interested in that to see Omar Abdelrahman's talk. He's going to talk specifically about that type of system. But there are many other types of systems out there. I'll show you one more. On the right side here is field effect modulation, which is essentially a field effect transistor. And if you're not familiar with these devices, you can actually just think of them as capacitors. In this case, I have a dielectric layer there in the middle, and the gate is just a metal that's inert. So it might be something like gold where we apply a voltage. Now, when you do that, you induce a charge in the top catalyst layer. So you can actually accumulate electron density or deplete it. And so what we're doing there is moving the D-band center of the metal with time. And that can actually happen very quickly. And it's already been shown that this can be done by my colleague Dan Frisby for the HER reaction to produce hydrogen. You can do this to make things like molybdenum sulfide behave more like platinum. It's a very cool technology and there's a lot to do. And it can be done in the gas phase. So Okay, so all of these different techniques, plus other ones I'm not showing you, they all are going to give you different scaling relations. And so we have to think about, well, which scaling type relation types do I want? Are there preferable different types of slopes and gammas and deltas that I would prefer? And so let's go back to this system here and just look at it. And what you can see is that, again, this is the same system I was looking at earlier, where I'm showing you the turnover frequency to be at different temperatures. But the more important thing is over on the right side, where I'm plotting the surface coverage, and you as a function of the binding energy of B. And of course, at high surface coverage of B, we're at strong binding. And as I weaken the binding energy, I then cross over to have a strong, a high level of surface coverage of A. As I keep going from right to left, I get weaker and weaker binding to the point where the surface is just open. That's temperature dependent, of course. So I'm crossing over there between surface coverages as I do the oscillation and binding energy. And I can actually think about this now in terms of different stimulating systems that will give me different scaling relations. So now the color scheme you're looking at here is this gamma parameter up on the top. And you can see a gamma of 1 means, in black, means that the two surface species move together at the same energy. They might be offset, but they'll move together. Now, the systems in blue are the high gamma systems, and those are the pictures I've been showing you. The systems in red are the low gamma systems. And so I can look at the surface coverage now on the left side of A and the surface coverage of B on the right side. And you can see that as I change this gamma parameter, I'm actually shifting how steep this transition is in surface coverage. And so you can imagine if I want to flip the surface coverage effectively, I would like as high a gamma as possible. And so I can tell you just from looking at this diagram alone that you want a very high gamma system if you can get it. You basically want to stay away from a gamma 1 where species move together, because you'd like to manipulate their behavior relative to each other. And there's equivalent plots here for the red species, the low gamma. Again, you want to stay away from 1. So if I put all these together now into a single plot, I can go back to this volcano plot and actually look at the turnover frequency to B as a function of this scaling parameter, the gamma that I'm looking at. And if you see what it's doing is it's sweeping out a range of reaction rates as I switch from a low to a high gamma, crossing over with 1. And what I'm going to do is I'm going to flip to the next slide where I show all of these possible volcano curves all together. So if I superimpose all of them together, the superposition of all volcanoes gives me a supervolcano. And you can actually see that it sweeps out this space on the right side, which is related to the desorption rate maximum, and the left side, which is related to the adsorption rate. And you can see basically then that every variation from the supervolcano results from a reaction rate limitation. So a perfect system would have no surface rate limitation, and it would be right at the binding energy there, where basically the reaction on the surface happens instantaneously. And you can actually see the gamma of 1 right there in the middle has this flat region where I'm not able to increase the rate at all. Now, of course, different stimuli give us different types of gamma systems. So the question becomes, how do these behave? And that's something we want to keep exploring and studying and understanding the relation between materials, adsorbates, and stimulating methods like light, potential, or strain. Now, what else can we do with these particular systems? We've been talking about rate, but we know that a lot of reacting systems, like the ones you see here, like ammonia synthesis, methanation, water gas shift, all have this problem of equilibrium conversion. So in this case, ammonia is favorable, the reaction in red, at low temperature thermodynamically, but it's kinetically accessible at high temperatures where the reaction is not thermodynamically favorable. And there are similar situations for many, many other reactions. And so the question becomes, how do we manipulate these particular systems? Right now, we think we have a reaction that's not thermodynamically favorable. We can pressurize it to push the reaction one way or another, or we can change the temperature, change the composition, all these kind of things. And what that's essentially doing is changing the overall equilibrium by changing the endpoint states. Of course, the other thing we could do is take our system under the favorable thermodynamics for a process, and then add work to the system that manipulates the steady state reaction in terms of the reactor performance. So if we add work to the system, this is this delta G you see here in the Gibbs free energy plot as a function of conversion. We would like to add work to a system and shift the steady state away from equilibrium to some new steady state by applying dynamics to the surface. Now, how does this work? Let me show you a simulation first, and I'll explain to you how it works. In this case, I'm showing you a batch reactor system where I have A going to B. This is that same model system I've been working with. And I can start out the batch reactor in many different compositions. So it could be pure B, it could be pure A, It could be any composition of mixture of A and B in between. And what I'm going to do is I'm going to let the batch reaction simulation proceed with time under this dynamic oscillation. In this case, my amplitude of oscillation is relatively small. It's only 0.2 electron volts. And so when I do that, you can see that no matter what composition I start out at the left side, my batch reactor system under dynamic conditions goes to a steady state of about 70 mole percent of B. Okay, and at some point in time, when I switch from dynamics to statics, the reaction goes right back to equilibrium, as it better have, or else there's some problem with the simulation. So that's our check to show that we're not violating equilibrium, we're just imposing some new element of work into the system. Now, the question is, well, how does this work? And this gets to an idea that's been around for a long time in many other systems, particularly biology. And that is that as we're oscillating the binding energy, we're creating an energetic ratchet, which can move species from one side to the other by actually lifting them and changing their binding energy with time. So we're applying work between the two different states of A and B. And of course, there's some efficiency to this because I'm getting some benefit out in terms of the apparent delta G relative to how much amplitude and work I'm putting into that particular system. Like I said, this shows up in biology. There's molecular pumps that move things into and out of cells. There's other Walkering type ratchet systems that move things along cells. This is all over. Biology found these types of mechanisms long ago. And what we'd like to do is think about how we could use them in heterogeneous catalysis. In this case, in this animation you see here, what's happening is in the strong bonding state, that's where the transition state energy is the lowest. And that's where the green will flip over and form the yellow. Now, as we go to the weak binding state up at the top, yellow species are able to get up into the product gas phase. And where the inefficiency comes from is that as we drop back down, some of the product yellow species are able to fall backwards into the hole. And there's a competition between green going to yellow and yellow going from surface species up into the gas phase. And some of these systems can be quite efficient, and other conditions are completely inefficient. You can actually see that in their performance, depending on the parameters that you pick. Okay, so let's look at one of these example systems here, where I've got an amplitude now. Here's a volcano plot where I'm showing you again the binding energy of B star as a function of the average turnover frequency. And I'm going to fix the amplitude that I'm actually imposing here, but I'm going to slide the amplitude left to right and say, well, which of these conditions gives me a favorable performance in my conversion? And in this case, what you're seeing here is the steady state conversion of my particular batch reactor. And you can see green here is actual equilibrium. So if I'm at very low oscillation frequencies, I get no benefit in pushing the system away from equilibrium. But as I move the amplitude from left to right, you can see that I go from a state on the left where I push it to very high conversions, and a system on the right in blue where I'm going to very low conversions. And you can see there's a very fine dividing line there between those two forward and reverse lobes in terms of overall conversion. So what actually determines that? And there's a lot of other things to pull out here, but the obvious one is where we go from forward to reverse. And it turns out there's a very simple explanation for how we drive something forward or backwards, and it has to do with the energy of the filling state of your catalyst. If you look here in blue, there's a forward and a reverse scenario, and what's actually very clear is when you're strong binding, which side of the surface reaction is at lower energy. So in the reverse case here, my A star in yellow here is at lower energy. I fill that more, and when I flip to the Umax red state, I'm removing that favorably. I reverse the ratchet on the right side by making the B star, the green state and the filling state in blue there, lower in energy. And so that's a relatively simple prediction here. By knowing where this transition happens is where yellow and blue surface species have the same energy. That's the delta point. And so I can actually find conditions where I can take reactions and move them forward or reverse and push them away from equilibrium by applying work of lifting them up. Now, there's one other place that dynamics can have a big role, and that's when we go from a single elementary step reaction to, in this case, we can look at multiple reactions, but in this case, I'll just look at two parallel elementary reactions. In this case, A could go to B as a product, or A could go to C as a product. And what I think about is if I have a system that's, let's say, 80% selective to one of these species, that's pretty good. But really, when you think about this conceptually, an 80% selectivity of a reaction under kinetic control just means that the favorable reaction is only 4 times faster than the unfavorable reaction. So a 4-to-1 ratio. And so the question becomes, what happens when I take one of the reactions and I make it go 10 or 100 or 1,000 times faster? My selectivity, my kinetic selectivity here should go significantly higher in terms of overall performance. So we can start thinking about 2 different reactions in a particular system. And I'll show you one here in the bottom right in panel C where I can think about how the two surface species change with time relative to A, and they have that crossover point there of delta BC. Now, when I do this, I can look at the plot on the left. These are the turnover frequencies of the two reactions. And it's very clear that it's relatively easy under static conditions to make product C. So if that's what I want to do, then this problem's already solved. But if I want to make product B, it's a lot harder because you can see that there's no scenario where I can selectively make B and not make C at all. And so the question becomes, if I apply this dynamic approach, is there a way to accelerate the production of B over the production of C such that it's favorable? And that's the panel over on the right here, where you can see I'm showing you the selectivity as color. So the selectivity to B here is red. There's that lobe of B that you see right there. The selectivity to C is blue, and the green is equilibrium here. So if we let this run for an infinite amount of time under static conditions, we would make equal amounts of A and B, which is the bottom right. And so while it's not normally possible to select for B, you can actually see that at low oscillation frequencies, that's going to give you the same outcome of a system under static conditions. The only possible scenarios are all C, blue, or green, which is equal amounts of B and C. And what's possible, even at low frequencies, you can see here at about 0.1 hertz, we're even able to get into this red zone at about negative 0.1 electron volts of left amplitude. And you can actually see that as you get up into the 10 to 100 to 1,000 range, it's possible to become almost perfectly selective to product B. Okay, so how does this work? We can think about this in terms of three different rates. There's the rate of conversion of A you see here on the left. And you can see that A is favorable in terms of overall reaction rate of the reactant under two different conditions. There's this lobe in the top left, and there's a lobe in the top right there. And then on the right, what we're showing now, these are calculations for just the reaction from A to B and just the reaction from A to C. And what you can see is that these two independent regions show up for the reactive rate, show up in each of the products, which essentially means that if I pick the right oscillation conditions, I can resonate one reaction or the other and make that more favorably at higher rates. Now, how does this work in terms? Why isn't this just a simple divider then between the two steps? Why do we have these complex behaviors emerging just from a simple A to B and A to C parallel reaction? And the answer has to do with the fact that there's two ways to think about this, and both of these show up in terms of competition. I'm showing you an energy diagram here from A to B and A to C. And you can think about the right side, where in that case, under the filling state, the strong binding, C star is lower in energy than B star, and it'll dominate the surface. In which case, if you dominate the surface, you will potentially dominate the products that are made. Alternatively, on the left side, you can imagine that B star in the weak binding state, the blue line there, desorbs much faster. So if C star can't come off the surface, essentially it might dominate the surface, but it can never be formed as a product. And so the balance between those two gives you the complex behavior that you see in these selectivity plots. Okay, so where is this going? Of course, we have all this effort in experimental work, and Omar's going to show you some of that in two talks. But there's all sorts of complex behavior from which the fundamentals are not known. What happens when you have reactions in series? We already know if you go A to B to C to D, that multiple waveforms here have the potential to allow you to accelerate these complex systems. But what about reactions in parallel, biomolecular reactions, complex mechanisms, or even bizarre dynamics where you have these negative gammas and many other possible systems? How are we going to possibly explore and understand how to selectively make one species out of maybe a complex network of 10? These are all open challenges in this area of dynamics as it proceeds. And of course, we can think about, what are the opportunities, which is really what I want to do. Can we accelerate reactions past the Sabatier maximum? I think we already know that that's possible using dynamics based on the work that Omar is going to show you. But can we push reactions past equilibrium? Biology has already shown this. Can we do this with heterogeneous catalysis? We'll find out. And of course, number three might be a big economic opportunity, which is, can we overwhelmingly control selectivity for systems where the selectivity has essentially been stuck for a long time at some selectivity amount that we have not been able to overcome with a static catalyst. Of course, there's so much to do here. There's immense effort still required, even just to understand complex reacting systems. How do the stimulating methods like light or potential or strain, how do they change with the chemistry in different materials? And then how do we get more complex waveforms that can take apart these complex reacting mechanisms? So I'm almost out of time here. So let me just thank, the two people that have done the computational work here. A lot of this was done by postdoc Alex Arda, who's written the papers you see over here on the right. And then Manish Shetty joined us last summer, who's also been doing computational work with us on these types of problems. And I'll put in a plug for them. They're both faculty candidates. So if your department wants to get in on this new area, you can get in right away by hiring two of the people working on this problem right now. But of course, let me thank also the Department of Energy who funds this work, and our whole Catalysis Center for Energy Innovation, where we get to work on these emerging problems as a team, where we can combine computation, material synthesis, and experimental work all together. And that's what it really takes to make these systems that are complex work. So let me end it there. And I know there's 4 minutes left to stay on time, where maybe we can take a question.
All right, thanks. Can you hear me now?
Yeah, I can hear you.
Okay, great. So we have 11 questions. So I'll try to summarize a few of them and read them to you. So the first line of questions is really, what is the source of the molecular resonance? Is this like matching the RPM of an engine to frequency of a tires, or something like that? And have you accounted or thought about the energy that's dissipated in damping the imposed oscillations?
Yeah, how do you think about this is the key question. And the way I think about it is this picture right here. Each of these elementary steps have their own natural speeds. And that's what you think of as these extending lines. And so the reason I drew this horizontally, this tie line in purple, because that's where I match those two time constants. They can each change, but I always want to match them up, because if I have one that's slower than the other, then I'm going to have an overall performance that runs at the slowest step. So I think of every particular elementary step as having a natural frequency, and I want to pair those up so that they're all the same. I want to maximize that as much as possible. Now, the second part of the question had to do with efficiency, and of course, I talked about efficiency in terms of molecular efficiency, but there's other types of efficiencies that I think you brought up in terms of like energy loss or some sort of damping energy that's lost. Those things definitely exist, and they'll depend on the stimulating method. It's something we're definitely looking at in terms of saying, how efficient is this? And of course, there's going to be more cost in doing this. And so the question becomes, does it make more sense to run a reactor at higher rates or better selectivity and save on the separations? Or is it better to do it a conventional way and pay for the separations? These are all process trade-offs that we're going to have to evaluate as we invent new technologies and try to find where the opportunities are.
All right, thanks. The next questions are kind of along the lines of, is there a way to determine if there's an ideal wave function or an ideal waveform that you can apply to this, and whether the turnover frequency is bounded if you had the perfect one?
So in an A to B system, it's relatively easy to say because the system is so simple, right? You're looking at it right here. For a given amplitude, there is an optimal frequency, and that's the frequency. It's half the frequency you read off from this particular chart, because there's 2 steps. For more complex systems, I don't know the answer for that particular question. What was the second part of the question?
Let's see. Is there, the first part was, is there an ideal waveform? And the second part is there a well-defined like upper end of what's possible here?
Oh, there definitely is. So you look at this picture that you're seeing right here with the simulation or the animation. You could imagine that these extend up further and further, and if you went to higher and higher amplitudes, you would push it out further. But at some point, these become completely unfeasible, right? If you went to incredibly strong binding energies, right, you might, if you have an oxide or an oxygen on a metal, you might just form an oxide. Or if you have nitrogen, you might form a nitride. Or on the reverse case, it's so weak binding, these systems become infeasible. So there's definitely an upper limit. Plus, I mean, even at those conditions, the amount of amplitude is just phenomenal. I mean, 1 electron volt of amplitude is enormous. I think experimentally we can get half an EV for sure, but can we get 1 electron volt? These are all things that we have to determine still.
Yeah, that's pretty extreme. I think in the interest of time and staying on schedule, we'll switch over to Professor Ulysses. I'm going to copy all of these questions into a Google Doc, and maybe Paul will find some time to maybe write some written answers for them, and we'll find a way to share those if we can. So our next talk will be given by Professor Ulysses, and he is a professor at Carnegie Mellon University and one of the co-organizers of this session. And he's going to talk about the scaling limits of scaling relation deviations on intermetallic surfaces. And Zach, I'll ask if there's a way you can put a pointer on your screen. A couple of comments in the chat have indicated, yeah, perfect. That would be super helpful.
Okay, thanks, John, for the introduction. You can hear me?
Yep, sounds great. Go for it.
Perfect. Okay, so Paul already gave a great introduction to some of the problems of scaling relations, so I won't really dive into why we're trying to circumvent these. But I did want to highlight there are a lot of different strategies, and I really like this paper by Javier and Nuria late last year in ACS Catalysis, talking about all the different strategies that we can use to break scaling relations. The things that Paul were just talking about is sort of up in the upper right. So these are dynamic effects, which could either be mechanical or electromagnetic or something else, dynamically controlling the catalyst or altering the properties. There's a lot of ways you can functionalize materials. And an area that has been talked a lot about is how to make a patchy or heterogeneous or bifunctional surface that has desired properties to get around some of these classical scaling relations. And so I want to talk about a couple of specific examples that aren't necessarily on these 5. So one is a class of materials called intermetallics, which are alloys that are strongly ordered. And I'll go into a little more detail why we're interested in these materials. And also p-block doped catalysts, which have been investigated sort of one at a time, but it's been a little bit difficult to get an idea of how their properties behave as a whole across all possible binary or ternary transition metals plus the p-block doping. So intermetallics are quite interesting for a variety of reasons. This is work that we're doing in collaboration with Rob Ryu, Mike Janik, and Zeke Liu at Penn State, funded by the DOE, and also work that we're doing with Shoji and Arena at Hopkins and UC Irvine, respectively, funded by the Sloan Foundation. So a couple of the nice properties are, first of all, these materials are very stable and very diverse. The formation energy can be very negative, which helps to maintain ordering and maintain composition near the surface. There has been a ton of work on the edges of this phase diagram. So at very low compositions of A or B, you get a solid solution alloy, and those have been really, really well investigated in catalysis. But at these intermediate compositions, you can get more interesting surface absorption sites and more interesting phases than what you would see in a solid solution. The next nice thing is that they're quite synthesizable. There are thermal and wet chemistry approaches for making these. If you go to an experimental collaborator who really likes making intermetallics, you can ask them to make a specific crystal structure and you don't have to worry quite so much about what specific phase you're using. They're verifiable, and that because of the long range ordering, it's a little bit easier to check that they are the crystal that you think they are with XRD. And also because they're ordered, sometimes you can get these really nice electromicrograph images that show exactly where the atoms are. And this is a case where there is perfect ordering at the surface for one of these crystals. And the final thing is, in addition to the base crystal structures, they're quite tunable, and that you can grow over layers on top if you want to add some strain, or you can make them hollow with different tricks. And so there's really a wide range of, there's a huge space here that we can investigate if we're trying to get around some of these scaling relations. And these sites look a little bit different than the solid solution ones that we saw previously. Okay, so scaling relation arguments in catalyst design often go something like this. This is sort of a simplified view. We do a lot of really detailed calculations on pure metal surfaces. This is an example from Jens's group, Chuan Shi and PCCP in 2014. This is a scaling relation between hydrogen binding energy and CO binding energy. For the pure metals, this looks really nice and clean. And we do scaling relations both for the thermochemistry and for the kinetics. And then we use that to build up microkinetics across descriptors. So this was follow-up work by Karen, who's going to talk later in Nature Communications for CO2 reduction. This microkinetic model is based on this linear scaling relation. There is a GCO here, and that is changing, but behind the scenes, the hydrogen binding energy is changing based on the scaling relation. And then once we have a plot like this, this tells us that there may be some targets that we should be going for. So for example, for CO2 reduction, maybe we want a CO binding energy at around minus 0.4 electron volts delta G. And this also says something about maybe the transition state. If we could tune that independently, we would want it to be about 0.7 electron volts for the transition state energy. Once we have those targets, then we can do a large scale screening via optimization. So we can either do high throughput and just find which materials happen to be in here, or we can do a targeted discovery effort if we can predict properties and then drill down on anything that we predict to be within this region. So in applying these ideas to intermetallics, there are some questions about how exactly do these scaling relations apply and how much can we trust them? Is this loop self-consistent if we have a patchy surface? So people have already thought about how we might want to tune CO and hydrogen binding energies independently. So Jan Rossmeisel had a nice review in 2017 where basically he pointed out that there's a class of materials that are all very strong CO binding and strong hydrogen binding, and they make a lot of hydrogen. You have some materials in the upper right that bind CO very weakly and bind hydrogen weakly, and you make a lot of CO or formate. And then copper in this region sort of has a privileged position, which has an intermediate binding energy. And so when we see a plot like this, and there's basically a hypothesis that we want to move beyond CO, when we're thinking about a new class of materials, really what we're asking is, what space might this class of materials occupy in this graph? And the underlying hypothesis is, if this new class of materials is actually interesting, maybe they would have some properties in this intermediate region and we could sort of fill in this area. But exactly how wide this area is and how far we can push this idea is really hard to nail down. And there's always the idea that maybe I should just search more intermetallics or search more alloys or something else. I also like this question that I saw on Twitter by James McCone. He asked in September last year, just posted, I think for a proposal that he was writing, is there such a thing as a catalyst that selectively absorbs hydrogen from a CO hydrogen mixture stronger than the CO? And so this question is really rooted in the idea that there is a scaling relation that we saw previously between CO and hydrogen. That's where this idea is coming from. And so on the same plot, what James is actually asking is it possible to find alloys or intermetallics that occupy this region in green, where the CO binding energy is actually weaker than the hydrogen binding energy? And currently, that's really difficult to prove or disprove for a class of materials. Finally, if we take that same microkinetic model that I showed before and we reformulate it in terms of the CO adsorption energy and the hydrogen adsorption energy, then we can see that there is actually an area with really high activity, sort of in this lower right region, and high selectivity. And so we really want to find intermetallics in this region. It seems like microkinetics back up this sort of qualitative argument that Jan was making. So how do we find intermetallics in this region? So we've had a system running online for about the past 2 years. The system runs every night. We're trying to find intermetallics with various properties based on descriptor arguments and otherwise. There's an automation component. We run about 200 calculations a day across different intermetallic compositions and surfaces. These are collected in a database. Over the past 2 years, we've done about 100,000 calculations across different compositions and surfaces and different types of sites and adsorbates. We published the CO and hydrogen data already on GitHub, and we're publishing the rest as they come out in papers. If you're interested, shoot me an email. So this runs every night, and we basically target different materials based on likelihood of having interesting descriptors for the chemistry that we're interested in. I'm not going to go into detail about each of these blocks. In order to make these predictions, we need models that can connect atomic structure on the left-hand side with properties like adsorption energy. And so again, without going into details, we can build models that directly do this. So we published this last summer. If you're interested, look in that paper. I'm also going to be talking about cases where we need uncertainty. And so with uncertainty in these same models, we published a paper in MLST in just last month with myself and a collaborator from the machine learning department in order to calibrate uncertainty estimates inside of these special machine learning models. The reason we need the machine learning estimates is because the space is so overwhelming that we can't brute force this problem. And so what I want to point out is when we're trying to figure out what is the adsorption energy on a new surface, a safe situation is one where we have multiple sites on the same surface, and the strongest predicted adsorption energy is one that we've calculated with DFT. And then we have a number of machine learning predictions for all the other ways that we could put an adsorbate on the surface. Maybe there's 3 other different sites here. We also need uncertainty estimates. And if all of those lie above the DFT estimate, then I would say this is a relatively safe prediction on what is the absorption energy for this intermetallic. If we don't have these machine learning models, we have a problem in that we might have a DFT calculation, but there could be another site that we haven't already considered, like a bridge site, that is actually lower than the DFT one. And so this is a situation where it is actually uncertain what is the absorption energy, even though we've done 2 calculations on the surface. And so for the rest of this talk, what I'm going to show you is a small subset of the data that we've collected. And it's only the surfaces where we think we're in the safe configuration region, where we have predicted a number of different absorption sites. And the lowest one among all of the predictions and all the DFT calculations is a DFT calculation, so that we can actually point to it and say this actually came from a specific functional, and we trust this number, and everything else we think is a higher energy. Okay, so moving into the data that we've collected, this is currently unpublished. We've done a lot of calculations on oxygen and OH for oxygen reduction. This is one of the simplest examples. It's a situation where we expect relatively strong scaling. So oxygen sitting on a surface binds to a central oxygen. OH sitting on a surface also binds to an oxygen. And so a very simple physical model says that probably if you strengthen the binding energy of this one on the left, you'll strengthen the one on the right as well. And so now this is a set of calculations. Every point is a prediction for a different intermetallic surface where the strongest absorption site was DFT calculated. There's about 500 or 1,000 points here out of about 500,000 different surfaces that we can consider across the entire intermetallic composition space. So these orange points are metals. Unsurprisingly, the metal one-on-ones obey a really strong scaling relation. Among all of the intermetallics, there's quite a bit more spread than the pure metals. And so the pure metals have a spread of about 0.3 EV. Among the intermetallics, that's a little bit larger. So we can shift this by about 0.5 EV up or down. The other interesting thing is that for this chemistry, oxygen reduction, the target, if we could break all the scaling relations, is at about 1.23 EV delta E and about 2.4 for the oxygen absorption energy. And so what this tells us is that it is not a big ask to find a material that has these optimal properties. We are on the edge of this overall distribution, but that is a very reasonable thing for us to search for. If I was a betting man, I would say that I can probably find materials in this region because we already have a few points close by. If we work really hard, we could probably find more points. Let's go to a slightly more interesting case. So this is another situation where we expect strong scaling. OH and OOH both bind to essential oxygen. And so we would expect there to also be a strong scaling relation, and this is the basis of a lot of oxygen reduction materials discovery efforts. In this case, it looks pretty much the same, but there are these outliers down in the bottom left that basically say it is possible to break the scaling relations as long as you have a material that binds oxygen so strongly that it goes into a bidentate configuration. And that's a situation that would have been difficult to find by hand, but sort of occurs naturally. If we're interested in that, we can fill it in. Unfortunately, this is still far from the peak in terms of OOH and OH. Let's go back to that CO and hydrogen scaling that was so perfect for the pure metals. So on these pure metals, we have a really nice linear relationship, but across all the intermetallics where you have different sites, there's actually a huge amount of spread between the CO binding energy on the x-axis and the hydrogen binding energy on the y-axis. We can deviate off of the scaling relation by about 0.15 or 0.2 EV, and more in some cases for some of these intermetallics. So this plot for intermetallics looks nothing like this really perfect linear scaling relation. And so that means that we probably have to go back and revisit some of the microkinetics if we're going to go to a bimetallic surface. James was asking, is there a catalyst that binds hydrogen more strongly than CO? And I've outlined this red region. That is basically the question that he was asking. And so after an analysis like this, based on the calculations we've done without targeting this area, I can say with some certainty, yes, probably you can find materials that are like this if you have a certain class of properties. All of these things we can also automate and put online. So let me just bring up really quick. So this is all sitting on Plotly. I'm happy to share the the plot afterwards. But we can go back and interrogate all of these things and look at where things were sitting, the formula, the coordination, what Miller index, where it was coming from, what the composition was. This makes it really easy to go back and play around for different chemistries. Okay. So like I said, we can also do the same thing for other materials that are not intermetallics. We haven't been focusing on these other ones, these p-block dope elements, but carbides, hydrides, sulfides, silicides, nitrides, we have a lot of data as well. Our preliminary data says that you can get quite a bit more deviation from scaling relation in these materials in the intermetallics. And this is unpublished data that we're currently working on. If you're interested in these sort of p-block dope elements, feel free to shoot me an email. Okay, so a quick summary. We're working to try and get property bounds for systems with diverse sites. And these intermetallics seem like they have a lot of possibilities for breaking the scaling relations, at least compared to the pure metals, as long as you have different anchorings. The pure metal scaling relations are not a great assumption for these intermetallics, so there's sort of an open area of literature here that we need to fill in. Carbides, hydrides, nitrides, sulfides can deviate a little bit more, but this is unpublished data we're still trying to verify and collect more calculations on. And if you're interested, feel free to shoot me an email. I'm happy to share the data, the analysis. We sort of have more than we know what to do with. And the next steps, I think, are really coming up with ways of defining rigorously what are the confidence windows on a class of materials. So can we guarantee or can we prove that we have found maximal properties for something like intermetallics? And basically, when do we know when to just move on and target another material if they aren't going to satisfy the properties we want? And the other thing is active learning to specifically target materials that break scaling relations is an open area of research. So with that, I'll just thank all the students and especially Kevin Tran and Perry, who did most of the calculations and did most of the data analysis that went into this talk, and various funding agencies that have funded this work. Thanks.
All right, thanks, Zach. We have one question right now, and that is, can you elaborate on the binding energy plots with respect to the work function of the metal? And they're particularly interested in how the binding energy for CO versus the intermetallic work function compares to any correlation of hydrogen binding energy versus work function.
Yeah, that's a great question. We haven't been calculating or we haven't been collecting the work functions from these, but that's something that we could go back and do quite easily. I think if you can come up with a local descriptor, you can probably make these arguments. But really what we're looking at is a surface where some elements like CO more strongly than the hydrogen. And so if you just look at work function of the entire material, you're probably going to get similar spreads, right? If you assume that there is one hidden variable behind this, you're not going to be able to explain all of the variation inside of the data set. But if you can come up with something more local, you can probably get at these arguments. That's basically what these graph convolution models are doing.
Okay. Speaking of graph convolution models, the next question is, does the graph model work for any chemistry, or do you make a separate model for each chemistry? I'm assuming what this means is that the question is there one model for all the intermetallics or a separate model for each intermetallic? Yeah,
that's a great question. There is one model for all the intermetallics. So in terms of the materials chemistry, there is a single model across compositions. That's the reason we're using these methods. That's a very nice property. However, we're currently building different models for each adsorbate. And so the CO model is separate from the hydrogen. We can use one model to train on both CO and hydrogen at the same time, but we currently don't have any data to suggest that it's doing any better than seeing the CO and hydrogen separately. And so coming up with improvements on this model structure so that you can either capture the prior that we know that there probably is some scaling relation between these adsorbates, or coming up with a system that learns from multiple adsorbates at the same time is something that we're really interested in and trying to work on now.
All right, I think the next question is, do you have any thoughts on why there's so much scatter in the scaling relations of the intermetallics? For example, is there a chemistry point of view or some variant that you're not accounting for? And if so, what would that be?
Yeah, it really gets at the fact that you have an ordered surface where you're exposing two different elements. And so unlike a solid solution where you tend to have clustering or it tends to be more of an ensemble effect, you can get really interesting behaviors. So here, for example, you have an edge site that is specifically just one yellow atom, so I guess nitrogen in this case. In a solid solution, you might not have only singlets or only nuclearity 1 sites. You might have a wider distribution that sort of averages out different effects. It's due to this really strong ordering at the surface and the fact that you have 2 different elements with unique properties that leads to this deviation. If you have a solid solution, that's much more well modeled with sort of a scaling relation argument.
All right, I think we'll do one more question, and then we'll break for lunch. There was a question about what parameters are you able to vary when you automate the generation of the different structures? How do you automate the different surface positions and terminations?
Sure. So we published an overview of the workflow that we have in JCIM in 2018. So I would refer to that. We also have all of the information on the automation up on GitHub. If you just search for Ulysses Group GitHub, the package is called Gatsby. It's all open source, running on open frameworks like Fireworks and other things. But I'm happy to go into more details. Just shoot me an email if you have follow-up questions.
All right, there's a few more questions in here, but I think we'll break for lunch or coffee or whatever your time zone finds appropriate. I will copy all of the questions into a Google Doc, and Zach, you can put some written responses there later. I think now we are on schedule for a break. So Omar, if you want to put the break slide up with the schedule, we will resume at 12:30. And at 12:30, Omar will be giving us the next talk. And we will resume with the afternoon's session with Omar, Hong Liang, and Charlie Sykes. Just a reminder for everyone, there is a poll that is up that is we put in to kind of capture what your thoughts are. And there is also a Google Doc that you can capture any kind of thoughts that you want to share or think about or otherwise capture for us. And we will have a discussion again at 3 o'clock where we try to brainstorm about future ideas for this. So there's the link to the Google Doc in case anybody wants to write anything down. And I'll see you all in about 27 minutes. All right, welcome back, everyone. We'll get started in about 2 minutes. All right, I'm going to start introducing Omar. Omar's a professor at the University of Massachusetts Amherst, and one of the co-organizers of our ATCAT meeting today. So this morning or earlier today, we heard a talk from Paul Downhauer laying out the whole sort of framework of dynamic catalysis and catalysis resonance. And Omar is going to tell us today about an experimental implementation of this idea using electrochemistry. So Omar, unless you have something else to say for the afternoon, the floor is yours.
All right, thank you very much, John. Thank you all for coming back and being here and making ATCAT a success today. So like John was saying, what I'm going to be talking to you about today is this idea of dynamic catalysis that you heard about from Paul earlier, still related to scaling relations and volcano curves, which Zach touched upon. And I'm going to try to convince you we can make use of this in a dynamic sense for this model system over here with formic acid decomposition to hydrogen and CO2 through electrochemical means. So without belaboring the point, we've heard about this in the last two presentations of why volcano curves exist and scaling relations. But we looked at the earliest case for which we know this kind of behavior exists, which is formic acid decomposition. So here I'm showing you what happens with thermocatalytic systems, where you can decompose your formic acid to either CO2 or CO. And if you look at this experimental data here, taken from the group of Israel Box, and you plot it against the D-band center of a metal as calculated by the Norskov group, you'll see this kind of volcano behavior, which has been frequently reported for this chemistry. And you tend to have platinum up here near the top of the volcano. And generally, it's thought that on the left-hand side of this plot, you're less weakly binding adsorbates in general. On the right-hand side, you're more strongly binding. And this has implications for the rate determining steps, or if there's a single one exists, and which one might exist on either side of the volcano. And we've seen that the same situation will exist for formic acid electrooxidation. So more or less the same chemistry. We are just using now electrons through applied potential to drive this oxidizing chemistry. And so this is experimental data from Radoslav Azdik at BNL, where you can see that the current also shows similar behavior, this volcanic type behavior. And here you can take current as directly proportional to the turnover frequency of a catalytic system. So our thought here was to take platinum with this model kinetic system and try to see if we can make use of this idea of dynamic catalysis and bouncing back and forth between either side of our volcano curve. Okay, so first things first, how does this chemistry proceed on the surface? You start out by adsorbing your formic acid on the platinum surface. One of the mechanisms that can proceed is through an OH cleavage first, and you have a formate species on the surface, whether monodentate or bidentate, and that releases a proton and an electron from the working electrode going to the counter electrode, where it will recombine to form a hydrogen atom on that surface. And then you can have a second step after that, where the formate undergoes a CH cleavage, another proton, another electron, you ultimately get your CO2 product. Now, alternatively, there's what's called the direct pathway sometimes, which involves this hydroxyl carbonyl intermediate, which starts out by having a CH cleavage happening first. And this rapidly decomposes, hence the direct name, to give you your CO2 desorbing from the surface. So these two pathways just differ in whether you have CH or OH cleavage first, but they're both purely Faradaic in the sense that every elementary step is proposed to involve a proton and an electron being transferred. Now, conversely, on the other side of this, you can have a mixed pathway or an indirect pathway, as it's called, where you started with a non-Faradaic dehydration of formic acid to adsorbed carbon monoxide. So no electrons or protons being transferred, just a thermocatalytic step. And then once you form your adsorbed CO, now the Faraday chemistry can kick in. You split water, you make an OH on the surface, and that will act as an oxidizing species for the CO to give you CO2. So regardless of the pathway that you take here, you're going to end up with the same set of products. CO2, 2 protons, 2 electrons, which will recombine at the counter electrode to make hydrogen eventually. However, the same cannot be said for their relative energetics. So if we look at just their delta E's and their activation energies for the various steps, what I want to bring your attention to is the CO-mediated pathway, which is just this thermodynamic well sitting down all at the bottom. Not surprising when you're dealing with something like platinum, and you have a very strong binding energy for CO. And what's interesting about this pathway is that you can readily make CO from formic acid at room temperature. This has been estimated with experimental measurements to be somewhere on the order of 10 seconds inverse. However, you have a very difficult time, not surprisingly, getting it off the surface because of that high binding energy. So here comes the idea of dynamic catalysis, where can we bounce back and forth between 2 energetic states, perhaps bouncing back and forth between 2 applied potentials, one where we facilitate the formation of carbon monoxide and one where we facilitate its removal. So research in this area has mostly focused on, can I make a catalyst that avoids making CO? What we're saying here is, let's lean into that. Let's use the catalyst in the way that it wants to behave and let it make CO and take advantage of that to drive our rate through this indirect pathway. Okay, so how are we going to do that? Just a quick background on this. We're using an electrochemical cell that's kind of like a CSTR in some sense. So you have a working electrode, which is our platinum catalyst, essentially. We have a counter electrode, which is where your protons and electrons recombine. And then you have a reference electrode, which just makes sure that you're applying the potential you think you are to the working electrode. And you have a purge of nitrogen going in to drive out your CO2 product, so you can detect that with gas chromatography and analyze your rates accurately. And we've put out the details of this in a recent preprint, which I'll have the link for at the end of this presentation, showing you how you can make this a gas-tight setup just using off-the-shelf liquid chromatography fittings. Okay, great. So the first thing we looked at is, how do things operate under steady state or at potential static conditions, where we can measure the turnover frequency here through chemical analysis, not through the current. And what we can do is measure the molar flow rate of CO2 coming out, normalize it by the moles of platinum we know we have available to us, which we estimate based on the surface area of our platinum that's available for catalysis, and an average site density of about 10 to 15 sites per centimeter squared. So once we do that, we see this volcanic type relationship between the turnover frequency and applied potential, where here I have the voltage versus the normal hydrogen electrode scale. And this is pretty common for what's reported for this chemistry on platinum. You get a peak somewhere about 0.5 or 0.6 volts NHE. And the reason that happens is still debated somewhat, but generally goes something along the lines of, on one side, I'm increasing my ability to oxidize my species on the left-hand side of this curve, but eventually I'm going to start making a lot of OHs on the surface, and that limits my ability to really keep the rate of reaction going as high as I would like it to go. So what we're going to want to do is oscillate between either side of this volcano to ultimately see if we can exceed what's available to us under steady state conditions. But before we do that, we want to confirm that what we're measuring is representative of the electrochemical reaction. because the tricky part is when you apply potential dynamic conditions, you can have a situation where you are constantly oscillating your potential and your currents could change as a function of something not to do with your reaction itself, but for example, charging or discharging your double layer. So we confirm this by looking at our current versus our extensive rate of reaction multiplied by Faraday's constant. And that should give you a straight line with a slope that's about 2 moles of electrons per mole of CO2. So that's in line with the stoichiometric ratio you would expect. So that's telling us the currents we're measuring are realistic in terms of the rates we are measuring for this reaction. Okay, so that's the static case. So now if we want to extend this now to a dynamic case, what we're going to do is start out our cycle at open circuit. And what I mean by open circuit, that's a condition where the switch is essentially turned off. There's no potential. There's nothing that can move in a Faraday sense. And the reason we do that is if you think of our chemistry pathways, only the formation of CO and the absorption of formic acid can proceed under these conditions. All of the other chemistries are kind of frozen out at this point. And then we can start out by using a square wave to oscillate our potentials where we instantaneously jump up to 0.8 volts, which was on the other side of the volcano curve. So the right-hand side of the volcano curve. And what we'll see is this sharp increase in the current, which is again indicative of rate. But that sharp spike is very short-lived. And what we think this has to do with, and we're not the first to report this, you're oxidizing your CO off the surface. So you're seeing the electrons are associated with making the hydroxyl species, but then using that hydroxyl species to kick CO off the surface and complete your catalytic cycle. But that's very short-lived because your coverage of CO rapidly runs out and your current falls back down. But we can keep applying multiple cycles and get this same current behavior multiple times in a row. And we can define two things here. We can define an average current. So this is the charge that evolves, the area underneath one of these current spikes, and normalize it by the time spent not only applying the potential, but the time at the potential and at open circuit, so time for one cycle. And that gives us an average current to wrap our heads on. And we can also define our frequency as the inverse of the sum of the time spent at both conditions. So let's put this to work. So what I'm showing you here is with time on stream, we're starting out under steady state conditions at 0.8 volts. And then I can instantaneously start to apply the square wave potential. And what we see is a rapid increase in both the turnover frequency measured by gas chromatography and the current as we're measuring by our potentiostat, where we see about an order of magnitude increase by oscillating, as I'm showing you in the cartoon on the left. We can then confirm what's happening here by stopping the oscillation instantaneously again, returning to potentiostatic conditions, and we see that our rate does drop back to the original condition, and the same story for our current. And we've also measured the residence time associated with our reactor, just the hydraulic residence time. And it's very much in line with these transients that you see over here. And ultimately, what we find is that the change in the current is similar to the change in the turnover frequency, telling us that we are in fact maintaining this 2 moles of electron per mole of CO2. So that's good to know. Okay, so the next question is, why does this work this way on a deeper level? How can we try to answer this? So we looked at some calculations out there by Mike Janik on this chemistry, where we could see that the non-Faradaic part is not going to be affected by your applied potential, the ability to make CO. But your ability to oxidize it is going to be strongly affected by your applied potential. So 0 volts, this is the situation. You've got a large barrier, and this 0 volts is essentially the open circuit potential. And then as you keep increasing the applied potential, your barrier decreases and your reaction becomes more and more exergonic. And so to quantify this, you can think about it in terms of this equation over here. Your delta E at any applied potential is equal to some standard state delta E, and it decreases based on the number of moles of electrons you have involved and the applied potential. Generally, you have 1 mole of electron involved for every volt of applied potential you give, you're going to decrease that delta E by about 100 kilojoules per mole. And then we can relate the barriers to this change in delta E through a BEP type relation, where I have a linear slope of alpha that's in between 0 and 1, depending on my transition state position. And I have an intercept, which is my athermal activation energy. Essentially, what's my EA when my delta E is 0? If I put all of this information together, this is kind of what we see here. So we have a scaling relationship based on the applied potential, where we see that we have a slope of about 1/2 as far as delta E is concerned, which is a pretty typical scenario for catalytic systems in general. And you see that the barrier drops somewhere about 80 to 90 kilojoules per mole for every volt of applied potential that you give your system. So conceptually, what we think is happening over here is that you are absorbing your formic acid, you are then forming CO, and this is the time you spend at open circuit, and then you apply a potential, and that lets you form your oxidizing species, and then you get your CO2 off the surface. So what we want to understand now is this what's happening, and also to be able to tune the time we're spending at both of these conditions to maximize our turnover frequency. So one quick proof I just wanted to show you is that we can do what's called a linear sweep voltammetry, where we look at how the current evolving changes as we ramp up the applied potential. So this is like a temperature programmed desorption, but with applied potential. And we get two peaks. The first one at a lower potential associated with the more purely Faraday pathways, and the second one associated with the CO oxidation of the surface. So if our hypothesis is correct here, what we should see is that as we spend more and more time at open circuit before ramping the potential, we should see peak 1 decrease and peak 2 increase. And that's exactly what we see here as we keep increasing our open circuit time. So it suggests the more you're at open circuit, the more carbon monoxide you build up, the more you will get of this second peak over here. So now putting this all together, we thought of this in two ways. So these are two different potential oscillations, one between physical open circuit, where we turn things off, and one between the applied open circuit potential of 0 volts. For reasons I'm happy to talk about at a later point when there's more time, this 0 volt as a potential is the same as the open circuit. But for hardware reasons, you have better control over the frequency with the red data over here. So focusing on that red data, what we're seeing is anywhere between a frequency of 10 and 100 hertz is where we appear to be maximizing the turnover frequency for this reaction, reaching about a factor of 50x over the steady state rate at 0.8 volts. And this is kind of in line with what we'd expect from the theory of dynamic catalysis Paul was talking about earlier, where I was telling you in the first few slides that CO forms somewhere at about 10 seconds in versus what the experimental measurements tell us from previous literature. And putting this all together, have we not only exceeded the steady state rate, we're also able to exceed the steady state rate of the volcano peak here by about a factor of 20x by using 100 hertz oscillation between the open circuit potential at 0 volts, where no reaction is happening, and 0.8 volts, where you're able to oxidize your CO off the surface. So in conclusion, by kind of understanding what the mechanistic pathways are and leaning into this CO-mediated pathway rather than avoiding it, we can take advantage of a potential dynamic catalytic system, and we can eventually get past what's available to us just under steady state conditions. And so with that, I want to thank everybody that's been involved, my group here at UMass, especially my first two graduate students, Ajibola and Han, who've been responsible for bringing the lab up to speed in under 15 months. And the postdoc that's done all this work, Josh Gopi Singh, along with Sean Burke, as well as our collaborators at the University of Minnesota, Paul Danhauer, Dr. Alex Ardon, Manish Shetty, and of course the funding agencies as well, the NSF funding this through an EAGER award, and the DOE through the Catalysis Center for Energy Innovation. And this is a link for the preprint I was just telling you about that we managed to get out just before the shutdown forced us to stop working. And if you have any questions, I'll be happy to take them.
All right, thanks a lot. We have a couple of questions here online. The first one that I want to ask is it going to be possible to match the appropriate resonant response for the reaction with the counter electrode? So if, for example, in a fuel cell or in a water splitting reaction, you may not have the same resonance response at the other electrode. So is this going to work when in that scenario, or is it only appropriate when you have like a counter electrode that's independent of those?
Yeah, that's a great question. So it would it would come down to what's really limiting you. If the counter electrode is what starts to limit you in any way, yes, you would likely find a different resonant frequency. The situation would likely become more complex. We don't know just yet what would happen. But yes, you're showing when the working electrode is what's limiting you and independent of how the counter electrode is performing.
All right, the next, maybe the next question is, have you been able to quantify CO coverage versus oscillation frequency, maybe by a stripping charge? And related to another question, how do you account for capacitive charging in the square waves?
Yep, both great questions. So we were in the process of trying to use quartz crystal microbalance, an electrochemical one. But hopefully as soon as we're let back into the lab, we'll be able to do that. Now, how I can answer this is through this linear sweep voltammetry over here. So as you spend more time at open circuit, you are oxidizing more CO, and that's the charge underneath this curve. So you can see the more time you spend at open circuit, the larger is the charge, the area underneath the curve associated with the CO stripping that's happening.
Okay. Let's see, I think we probably should transition over to Hong Liang. And while we're doing that, we'll take maybe one question about the on and off times of the waves and the frequency. Could you comment on any work you've done in changing the spacing between the waves or anything like that?
Yes, that's a great question as well. So this is in the context of a duty, what we call a duty cycle. We have started looking at that. So spending asymmetric amounts of times at open circuit or the voltage. So far, we've seen that this 50% duty cycle or equal time is the best, but we haven't explored a large enough space, but are definitely planning on doing that.
All right, great. So Omar, why don't you stop sharing and Hong Liang can start sharing his. For everyone else who asked all the interesting questions, I'll capture these and give Omar a chance to provide written responses later. And these will all be separated by the presenter. So hopefully it'll be easy to read those at a later time. All right, so our next speaker will be Hong Liang Jin from Virginia Tech. And he's been looking at a couple of ways to model electrocatalysis where we want to tune the adsorbate properties. And he's been investigating a Bayesian modeling approach to doing this. So thank you, Hong, for coming. And whenever you're ready, the floor is yours.
Thank you, John. Can you hear me?
Yeah, sounds great.
Great. Thanks for organizers for giving me this opportunity to share some of our recent work on developing physical models to understand how the scaling exists and how we can potentially develop some strategies to go beyond the linear scalings. In this approach, we are going to use the Bayesian inference to learn some the model parameters. So just some simple background for people that came in. So in heterogeneous catalysis, of course, we care about what's happening on the surfaces. If you zoom into the catalytic interface, there are a lot of elemental steps could occur. For the reactors, they have to absorb on the surface and possibly dissociate and activate it. and diffuse to the active sites and form some new chemical bond eventually dissolve into the gas or solution phase. So I want to emphasize how strong, how stable the intermediates on the surface is really a critical indicator if the catalyst is working or not, even without looking at some kinetic barriers, simply because absorption energies are intrinsically correlated with the activation barriers through the BP correlations. So, so these are very general slides, very general phenomenon observed in heterogeneous catalysis on metal surfaces. So simply they see that for the absorption energies of the common intermediates, if they're bonding through the same item, most likely they are linearly correlated. So they show that on a few different transition metal surfaces, even with different atomic structures of the active sites. So this phenomenon we see on not only carbon, nitrogen, and some other oxygen bonded species, and even some others. So interestingly enough, so the correlation, the linear coefficient is dependent how many unsaturated electrons or bond that you can form with, for example, hydrogen. You can see here the for oxygen and OH. So they roughly have half scaling coefficient there, because oxygen have they can have two valence electrons, can form chemical bond, and OH have one. So from some simple understanding, we can know why they have a linear correlation. But what's one of the important consequences of this type of linear correlation is the Sabatier principle. So basically, the optimum catalyst is some sort of in the middle of the molecule surface interaction energies. You don't want to absorb it burn too strong, that will limited by the absorption of the product. You don't want to burn too weak, then they have a hard time to activate a strong chemical bond. So you want something in between. So it's basically how strong this molecule or sorbate interact with the surface is really the critical factor to control the catalytic processes. And if we can understand the fundamentals of the chemical bonding, hopefully we can understand the fundamental limits of the linear correlations and figure out the physical way to go beyond it. So that's the main scheme of my work here. So just one example for this linear correlation, I'm interested in the fuel cell catalysis. So for this reaction, you have to transfer for proton electron to the O2 to form water. So on the right, it shows basically the measured oxygen reduction activity from model surfaces as a function of OH binding energies. You probably see something like this type of volcano curve before. So basically the microclimate model, the dashed line showing here, and also the measurement, they see something interesting that basically the OH is a very good descriptor. You can compare to pure platinum, if you can weaken the OH binding energies, and then you can have a better performance. But there is a limit. If you go too weak to the OH binding to the platinum or the active sites, then they become limited by the first step to protonate the O2. So this linear correlation is really the problem. Ideal case, if you show here, if you see here the free formation energy linear correlation of OH with the OH and atomic absorbed oxygen here, in the ideal case, your OH free formation energy is about 1.23 electron volts. So you can operate at so the last step of OH desorption can be operated as the equilibrium potential. But for this ideal scenario, you have to stabilize the OOH by a few amount, by a significant amount compared to the scaling line determines. So that's really the challenge. So how can we, is it really possible to break scaling between this OH and the OOH? So in order to answer the question, we have to look at it, the chem absorption model. So of course, the state-of-art chem absorption model is the D-band model. I'm showing some schematic here on the left. If you have some valence state interacting with the metal surfaces, and the metal surfaces are characterized by some delocalized S states and some narrow distributed D states. So first step, then the interaction of the adsorbate with the broad SP state can form some resonance states. And following that, they can interact with the narrow D states, forming these bonding antibonding states. And occupancy of these antibonding states really determines how strong this chemical bond is. If you have some metal surfaces that have a lower D band center, then you can imagine the antibonding state will become lower in energy, get more populated, so you can have a weaker chemical bond. So on the right, it shows some experimental evidence about the theory really validate what you see on the left. And another evidence to show you briefly, this is you can think about this is the hydrogen absorption energy versus the D band center of active sites. So on a range of model surfaces of the palladium on different type of substrate, you can see D band center is really linearly correlated with hydrogen binding energy very well. But this is only so D band model can give you a really nice qualitative understanding about the chemical bonding. But in order to understand the fundamental limits of scaling correlations and how to go beyond that, we would like to go a little bit deeper and more quantitative understanding about chemical bonding. So then we have to go back to the initial Newton model that can give you a more quantitative understanding about chemical bonding. So this is a picture, you see it already. So basically, Newton model can help us to understand how this, for example, this adsorbed resonance state or adsorbed energy level interact with the metal surfaces, forming this bonding state and antibonding state, and what's the formula to evaluate the binding energy of this type of interactions. So this is some sort of a parameter we have to introduce, but I don't want to bother you with too much details. So basically, the Hamiltonian on the top includes some one-electron energy contribution from the adsorbates, from the substrate, and the coupling between those two set of states. And you can, if you know some parameters in the Hamiltonian, you can solve it within some one-electron approximation using Green function approach. There are two information you can get out of it. One is density states projected onto your adsorbate valence orbitals. I can have this formula here. Another information that you can derive is how strong this adsorbate bond to the surface, which could include the SP band contribution and also D band contribution. And SP band contribution, typically in the model, we assume to be a constant value on the transition metal surfaces. And for the D band contribution, we can separate in two different parts. One is the one electron energy contribution that I can just simply integrate into the states. Another is the repulsion energy contribution that is really proportional to how large overlap of the two set of states is. So in this simple model, there are a few different parameters I want to briefly touch upon about it. One is basically this where is the adsorbate energy level is. So you can imagine you have a few frontier orbital of adsorbates, and what's the energy level relative to the work function or firm level of your substrate. Another is how strong the coupling is, this VAK. So that's really determine the energy change of the interatomic coupling. And I should point out that the relative value are really tabulated on the book. And the last parameter is the overlap between the adsorbate states and the metal states. So that kind of influence the orbital orthogonalization energies when they come together to interact. And for the metal states, we simply use the DFT calculated projected states onto the metal D states. So for these fault parameters, you can use more deterministic fitting to get those parameters with some training data. But I would like to take a Bayesian approach. So in this approach, So basically, you can see this is the Bayes theorism. So basically, what you want to figure out is what's the probability distribution of those parameters for given evidence or given data sets. And for our time absorption models, the observation is the DFT calculated absorption energies and the density states. So the important advantage of Bayesian approach is you can incorporate the prior knowledge if you have for each parameters. And this is basically the likelihood of observation for given parameter site. And the PE is normalizing constant in the Bayesian optimization. So this constant is really difficult to calculate directly. So you can use Markov-Chain Monte Carlo sampling approach to sample the partition distribution without considering this normalizing constant, simply because in the Markov chain hopping, the probability of each step is only determined by the relative probability, not the absolute values. So this approach, you can have less prone to trapping at the local minimum. So we use this the Bayesian optimization in PyMC with about 100K training steps for oxygen on pure metal surfaces. We have about 9 transition metal surfaces. So this is a learning result. So by training those density states and absorption energy of oxygen on those pure metal surfaces, we can derive the posterior distribution for those 4 parameters listed here. So they all have a very nice Gaussian distribution with some uncertainty on each parameter. And some parameters there's some correlations between them, but most of them are independent samplings. So one of the advantage of the Bayesian optimization is that you can evaluate uncertainty of the model. So here just showing the DFT calculated green line, the density states projected onto the oxygen 2p states, and the blue is the model predictions. So for oxygen, we only consider one frontier orbital with oxygen 2p, designed 2p states. So for this simple model, we can really capture nicely the main features, including the bonding states and anti-bonding states for a broad range of the pure metal surfaces, really nicely. So in terms of energy, so this is the DFT calculated oxygen binding energy on those metal surfaces, and this is the model prediction. We have about 0.1 EV root mean square error. And for each metal, we can evaluate, because the parameter side we have from the Bayesian learning distribution. So you can evaluate the standard deviation of the model prediction. So basically, this really nicely put the error bar on the model prediction to see how reliable of the model is compared to the DFT calculated absorption energies. So from here, basically we have a reasonable model to capture not only the quantum structure but also the bonding properties for the oxygen on metal surfaces. We did the same thing for OH and OH, so we're not going to show them here. So we can learn a lot from the physical model. So sorry, this is the basic slides. So the question we are trying to answer basically is why the OH and OH are strongly correlated. So if you look at the left graph, so this is showing the OH absorbed on these 5 metal surfaces. So the blue point represents the hybridization energies, including the interaction with the SK states and also the localized D states. So they roughly linearly correlated to the interatomic coupling metal element, basically how much the coupling of the absorbed this oxygen 2p states with the metal D state. And also for the Pauli repulsion, this shown on this red point, it also linearly correlated to this parameter. So we observe the same thing for OH. So basically for both the repulsion energy and the hybridization energy, they are linearly correlated to this interatomic coupling metal element. That's why they are strongly correlated in nature. So we can learn a little more if is it possible to break scaling between these two different adsorbates? So the question basically trying to answer here is, for example, if you want to shift the d-band center of the platinum or any metal by a small amount, simply perturb it without changing all the other power moments of this distribution. So how does it affect your binding energy in terms of the oxygen and OH and the OH? So here we are using the OH and OH example shown here on the right. So for different metal surfaces, what we see here is so basically you move up and down the d-band center, even though you're not influencing all the other moments. The binding energy are still linearly correlated on this parity plot shown here. So that means if simply perturbing this d-band center of the metal site of these states, you're not going to break the linear correlation between OH and OH. So that's really give you some sort of fundamental understanding which parameter is really the parameter we can play with. But unfortunately, we did all the other moments, and I'm showing here them on the right. So we can perturb not only the center, we can try to perturb the width and skewness and kurtosis of the d-state distribution separately. And what we see here is, so this shows the sensitivity analysis of the basically tell you how the absorption energy of different intermediates responds to the electronic structure perturbation. We can see here the two adsorbates almost have a similar sensitivity to d-state perturbation up to fourth moment. And above the fourth moment is really difficult to manipulate in kind of design. So so basically the question, the answer we're showing here is so basically it's difficult to break the scaling of the OH and OH by simply perturbing the metal d states distributions. And one interesting thing we see here is for OH and OH, it turned out the third moment playing a more important role than the lower moment. That's something we are trying to understand further to see if we can explain a little bit better in terms of how the influence in the states and the chemical bond. So this is a conclusion slide, a quickly summary. So by learning from DFT calculated electronic structure and the absorption energies, you can develop some physical models with some uncertainty quantifications as shown on the right. And another thing, the benefit about physical model is you can infer some physical insights from the model, see how different factors and influencing the chemical bonding of different adsorbates, and to see it's really possible to break scaling by changing different electronic structure of the surface sites. And by using the OH example, what we see here is really difficult to break scaling between the two different adsorbates simply by a monofunctional site anonym. So that suggests us maybe we have to go beyond this simple site tuning to leverage some multifunctional adsorption sites to possible to break scaling. So this I want to acknowledge the funding from NSF Catalyst program, and my students Siwen Wang and Hemang and also Nushin, they did all the work. And finally, I want to acknowledge the community resources from Virginia Tech. So so hopefully I have some time to answer your questions.
All right, thank you very much, Hong Liang. We've got a couple of questions. Unfortunately, in the interest of time, we'll be posting these questions to the Google Doc you all have access to, and we'll be forwarding those to Hong Liang so you can provide a written answer for those.
Okay.
Thank you, Hong Liang.
Thank you.
All right. So next up, we have Professor Charlie Sykes from Tufts University. He's a professor there at the chemistry department, and he's going to be talking to us about their work with single atom alloys and all the unique properties they have for the ability to break linear scaling relations. And just one note before you start, Charlie, if you could hit the display settings and switch to presenter mode, because we're seeing the opposite on this end over here. So the display settings for your power, yep, there. And yep. It's a little cut off. So if you could try exiting your full screen and entering again.
Any better?
Yeah, if you can just try that swapping that presenter mode one more time. Yeah, perfect.
Okay, you can hear me okay?
Yes.
Great. Well, first, massive thank you to the organizers. It's such a wonderful break to the monotony of sitting home alone to be listening to all these interesting talks. So thanks so much for putting it together. So I'm going to tell you a short story today about what we call single atom alloys and really try to focus on opportunities for breaking these linear scaling relationships. But I'd like to start by dedicating this talk to my late friend and colleague, Maria Flitzani Stephanopoulos, who passed away in October. And this is actually a picture of a lot of us from the last ACS meeting, which was just in August in San Diego. So as a very brief introduction to the area, heterogeneous catalysis, as you all know, is a very complicated topic, all the way from the large scale reactor design and optimization, all the way down to the atomic scale structure of the active sites themselves. And that's where chemists like me are really interested in understanding structure function relationships in terms of the atomic scale structure of the active site and how that affects the chemistry of the reaction. So there's many great heterogeneous catalysts operating as we speak in industry, but there's still room for improvement. In particular, a lot of the elements that are really good catalysts like platinum, palladium, rhodium tend to be fairly scarce in nature and therefore expensive. So there's not enough platinum for everyone to have fuel cells in their cars in the future. Not every reaction in industry is 100% selective to the product, so there can be improvements there. And then deactivation of catalysts over time due to coking, carbon buildup can lead to inefficiencies. And then CO poisoning as well limits conversion in the startup of three-way catalysts. So the talk I'll give today will hint at this new architecture of single atom alloys, being able to address all of these outstanding issues. So this is what a typical heterogeneous catalyst looks like. It's sort of this black dust. They're very complex things because they have all different types of metal particles, atoms, oxides, promoters, alloys, all these different variables. So it's very hard to sit down and rationally design a better catalyst. And that's why we're all on this meeting today, because for years people have thought of ways to understand how heterogeneous catalysts work. The volcano relationships are a very useful way of understanding it in terms of balancing the binding strength of your intermediates or your reaction energy with the activity of the catalyst itself. And as you can see there, platinum and palladium, these expensive elements come towards the top. And they're really underpinned, these relationships, by Bronsted-Evan-Polanyi plots, which really show these nice linear correlations on the single metal, pure metals, where you're looking at the reaction energy of each particular reaction step and correlating that with the activation energy. So you see that the stronger you bind, the more exothermic the reaction step, the lower the activation energy and the faster the rate. So that's great in terms of really bringing forward the understanding of how things react on catalyst surfaces. But in the way we're all talking today, you're still stuck with these linear scaling relationships. What you'd want to have is you'd want to have catalytic metals or other with points down here. So lowering your transition state or your activation energy while keeping the weak binding of the intermediates on the surface. You'd really want to be looking for points on the underside of the scaling line. So one very nice example from theory from Manos Mavrakakis's group from over 15 years ago of potential for escaping these linear scaling for the pure metals is for hydrogen dissociation on what are called near surface alloys. And this is where you have a single layer of one metal on top of the bulk of another, or sandwiched between the top layer and the bulk of another metal in this sort of sandwich structure here. And what Manos is plotting here is the line here is for the single 111 surfaces of the noble metals, where you have a correlation between the binding strength of hydrogen atoms on the surface more strongly bond this way, and a lowering of the transition state energy for activating the molecular hydrogen. And what he's plotted here is for a lot of these near surface alloy combinations, you can dramatically reduce your activation energy for dissociating molecular hydrogen, but also keep the weak binding of the hydrogen atoms on the surface so you can get both things that you want. And that's a very exciting result. It's harder to implement generally because it's hard to make core cell structures, and then even harder sometimes to keep them in this, or particularly this format during reaction, because under reaction conditions, these may restructure. This blue element may come to the surface if it binds more strongly to the intermediates. So in my lab, we've taken a different approach. Because we work in ultra high vacuum, we have scanning tunneling microscopy. We can examine surfaces with atomic scale resolution. And what we've been doing for the last 12 years is to take a less reactive host metal like a copper 111 surface, you see atomically resolved here, and then put tiny amounts of palladium, for example, more catalytically active elements into it, where basically one copper atom pops out and a palladium atom takes its place. And that's what we term a single atom alloy. It's an alloy at the atomic scale where you have just single atoms of another more reactive element replacing some atoms of the host metal surface. And today I'll try to convince you that these single atom alloys generally can escape these linear scaling relationships. So we start the experiments with our host metal surfaces. Typically we use copper or gold or silver, which are more inert, weaker binding metals that typically exhibit high selectivities, but low activities in the reactions they catalyze. And then we look at the periodic table and we look to the left of those elements and we find more reactive dopant atoms we can alloy into the surfaces. So palladium, platinum, nickel, we're now onto rhodium. And what we find in some cases like palladium gold, platinum copper, palladium silver, nickel gold, is that we get this nice atomic dispersion of just single atoms substituted into the host surface. Other combinations like silver copper don't mix too well at all, where you get mostly separated domains. And then this case of platinum gold, you actually see you've got both single atoms and small clusters. And it's really due to the mixing enthalpy, where the ones that form single atom alloys have a negative mixing enthalpy. So for example, nickel would rather be surrounded by copper than other nickel atoms. So the thermodynamics drives the atomic dispersion of these. Whereas I'll show you later, platinum and gold have pretty much zero mixing enthalpy, which means the formation of single platinum atoms or clusters is equally preferred, and that's why you see a distribution of sites. So if you can do catalysis this way, you can obviously make a big cost saving if you have something like platinum alloyed in copper, because of their vastly different price differences. And like I say, a lot of the experiments I'll show today are working at the 1 or 2% doping levels of the expensive reactive element. So we start with incredibly clean surfaces, and I'll talk today about copper. And it's very important to have a clean surface because you don't want to be looking at the reactivity of minority defects in these surfaces. So we can clean these surfaces in ultra high vacuum to better than 1 part in 10,000 atoms. And then we basically heat up samples of palladium, for example, that you evaporate small amounts of palladium, the atoms fly through the vacuum, land on the copper surface, and you can see in the STM image after the alloying has been done that around the monatomic step edges, you see all this rumpling. But if you zoom in with atomic resolution, and again, we've only put 1% palladium into the copper surface, we see some single atoms in the surface and some single atoms underneath the surface. So the ones in the surface layer are slightly brighter here, and the ones underneath are slightly darker here. And depending on the temperature we make the alloy, so just above room temperature, you get palladium imaging like bright spots. Now they're not palladium atoms on the surface because STM is so sensitive to the Z direction that they're only about 10 or 20 picometers higher than the surrounding copper. So this is showing the side view of this surface where the palladium atoms are substituted into the copper surface. And then if we go to a higher alloying temperature at 500 Kelvin, you see mostly dark spots there. And that's because palladium has a higher surface free energy than copper. It has more of a tendency to be surrounded 12 coordinate by its host. So thermodynamically in a vacuum, palladium would rather be underneath the surface or in the bulk as apparent here. But then what we know from high pressure XPS work, for example, is that if you have a surface like this with a catalytically active element under the surface or in the core, if you run a reaction over the top or flow things like carbon monoxide, those elements will actually be stabilized back at the surface. So the thing to remember is alloys are very dynamic, just above room temperature in terms of how they respond in their surface composition as the reactive atmosphere is changed. The important thing here is that you don't see any long range order, but you can stare at these images all day. You'll never see at the low coverage regime any palladium dimers in this copper surface because of that negative mixing enthalpy of palladium and copper. It would rather be surrounded by copper. So again, it's really the thermodynamics that drives the atomic dispersion. Now to talk about the first class of reactions, hydrogenation reactions, because you quite often want to be selective in these reactions, you don't want to run your catalyst too hot in temperature. And in that case, hydrogen activation can be rate limiting. So let's talk about the energetics of hydrogen dissociation on pure copper and pure palladium, and then look at the mix. So on pure copper, hydrogen will not dissociate in a vacuum. You actually need a molecular beam to bring the hydrogen molecules in with higher energy in order for them to dissociate on the surface. But once you do, they'll recombine and desorb with regular second order kinetics. Whereas on palladium, easy to dissociate molecular hydrogen. You can get plenty on there below 100 Kelvin, and again, second order desorption. But if you looked at these two temperature programmed desorptions, you would see that the temperature which the hydrogen comes off the surface is almost the same, and you would naively think the reactivity of these two metals towards hydrogen was almost identical. But what we know from other measurements, beam measurements in theory, is that hydrogen dissociation has this high barrier on copper, but once the hydrogen's dissociated, the hydrogen atoms are bonded weakly to copper. Whereas in palladium, there's almost no dissociation barrier, but then the hydrogen atoms are bonded much stronger to palladium. So the question is, what do you have when you have just single palladium atoms? And just to make a note about the temperature programmed desorption, the reason they both desorb at 300 Kelvin is to basically recombine the hydrogen atoms on the palladium. Takes this amount of energy, is about 300 Kelvin. And then microscopic reversibility says that on copper, you have to come back over that dissociation barrier to desorb. And again, that energy is about 300 Kelvin equivalent in a desorption experiment. So the question is, what does the energy landscape look like when you have just single palladium atoms? And what we find is that 1% palladium atoms in copper, you can uptake and dissociate hydrogen. And most excitingly, it actually goes on and off the surface 100 Kelvin lower in temperature than on either pure copper or pure palladium, as you see there from the desorption peak. So it turns out the energetics for dissociation and recombination look like this. You have almost no dissociation barrier that we published years ago with one of our hosts, John Kitchen. And then you actually have weak binding to the hydrogen atom, because the hydrogen atom bonds mostly to copper than to palladium because it sits in a threefold site. So it means where it sits has a binding strength more similar to copper than to palladium. And it's also so weakly bound it can spill over onto the copper surface, which I'll show in a minute. So here we're showing for hydrogen dissociation for a palladium copper single atom alloy, we've broken linear scaling because we have both things we want. We have a low activation barrier and we have weak binding of the hydrogen. And the reason for that is that the location of the transition state and the final state for the dissociation are decoupled. So in a simple sense, the transition state is benefiting from the palladium atom's electron density in order to lower that energy, whereas the final state has the hydrogen atoms bonded to 2 copper atoms and 1 palladium. So it has a fairly weak binding strength, which decouples the two and allows you to have low activation and weak binding. And more recently, a group led by Mikhail Stamatakis at University College London has computed Bronsted-Evans-Polanyi plots for the pure metals for hydrogen dissociation, as seen here in blue, and then for a lot of single atom alloys seen here in red. And what you can see is that there's no real linear scaling anymore. There's a big cluster of points here. But most excitingly, it lies on the underside of the curve, which means for all these combinations, we should have a faster rate of dissociation of molecular hydrogen while keeping the weak binding of the hydrogen on the surface. Now, if the hydrogen can spill over from the final state here onto the copper surface, the situation gets even better. For example, if that's palladium copper there, if the hydrogen spills over, it'll have binding strength similar to pure copper, which is here. So it'll actually move this point all the way to there. So you'll have even weaker binding in the hydrogen and a low dissociation barrier for the activation of the hydrogen. So we can go look for hydrogen atoms that have spilled over with the 5 Kelvin scanning tunneling microscope. And this is an image showing that this is the region where the single atom alloy is with the palladium atoms above the copper step. And you see the whole surface is now covered in these small brown depressions, which are individual hydrogen atoms on the copper surface, even far away from the area where the system is alloyed. This is all pure copper, as you see here from the standing waves. You have these two-dimensional puddles of not molecular, because that would desorb, of atomic hydrogen atoms on the surface. And we can image the dynamics of these, and you can see the fast diffusion of the hydrogen atoms on the copper surface here. And it turns out that's actually mediated by quantum tunneling in the diffusion, through the diffusion barrier. Because if you do the same experiment with deuterium atoms, you can see on the right here, the rate of diffusion of the deuterium atoms on the surface is a lot slower. So I hope here I've convinced you that just by depositing molecular hydrogen on these single atom alloys and then cooling all the way down to 5 Kelvin, where we can image the hydrogen atoms, that they have dissociated at the palladium site, but then spilled onto the copper surface where they're weakly bound. And then we can test the reactivity by, this is just a model reaction trying to hydrogenate styrene to make ethyl benzene. And we see that on the single atom alloy surface, we get 100% selectivity to the ethyl benzene. Another example is for a more relevant reaction, hydrogenating acetylene to make ethene. It's 100% selective, whereas if you do the same reaction on a surface that contains a monolayer or two of palladium, as seen here in the STM, you only get 33% selectivity to ethene. You get all this high temperature hydrogen, which means that you've left carbon behind on the surface and decomposed the molecule you've tried to hydrogenate. And this is really a stark example of an ensemble effect, where in the single atom alloy case, you only have single palladium atoms, which are able to dissociate hydrogen, but they're not able to decompose your reactant because palladium will overbind acetylene and basically break it down to carbon. And that's why you see this hydrogen released here. So in the single atom alloy case, you can break the bond you care about, the H2 molecule bond, but you don't dissociate the molecule itself, which leads to coking and deactivation. So is this effect general? I've told you that story about palladium copper. So we moved to platinum because platinum's ubiquitous in many different important chemical reactions. And we chose this reaction here, which is the selective hydrogenation of butadiene to butene. This is important for the polymer industry, which tries to take this impurity out of propane feedstocks for polymerization. So you really want to make butene, but not butane. And what we see on a 3% single atom alloy platinum copper surface is we see 100% selectivity to butene, no butane, and no high temperature hydrogen. So we're not decomposing the molecule. So that looks very promising. And then what we can do is show turnover in UHV, where we basically do the same experiments 18 times in one day on the same surface, and we basically get the same high conversion to the product. We see the same uptake of hydrogen, and we titrate the platinum sites as well. So you can see that multiple cycles on this surface do not lead to poisoning as it would be with a platinum or palladium surface. And now, because we have the scanning tunneling microscope, we can ask the question, where does each reaction step occur? So this is STM on the left here, which is basically shown in this cartoon here. So this is an experiment in which we have platinum atoms on a copper surface. We've exposed it to hydrogen. The hydrogen is dissociated, spilled over. Hydrogen's the red dots here. And then we've absorbed a little bit of CO, 1 or 2%, to just selectively bind to the platinum sites because it binds to copper so weakly. So what you see here is the black circles here are the CO molecules absorbed on the platinum atom sites. And then all the streakiness around them is that fast diffusion of the hydrogen through quantum tunneling. So basically, I'm just showing you this model should be correct. Then we image it slightly higher bias, which basically sweeps the hydrogen away from the area. And now you just see dark spots there, which is every platinum atom as the surface is capped by CO. And then we pulse each CO molecule at 5 volts, tunnel into the LUMO, desorb the molecule, and then you can see the position of every dark spot here. Underneath it, there's a little bright spot, and that's the platinum atom in the copper surface. So this basically just tells you that the hydrogen spilled over onto the copper and that we can selectively titrate the platinum sites with CO. So in the next experiment, what we did is we ran the reaction without CO, and then we put 1% CO on the surface after the hydrogen had spilled over, and we ran the hydrogenation reaction through a temperature programmed desorption. And what we see in both cases is the same conversion of butadiene to butene, whether the CO is on the platinum or not. So what that means is that the hydrogenation step of butadiene to butene happens on the copper, whereas we know that the dissociation of molecular hydrogen happens on the platinum because we put the CO there first, we don't dissociate the hydrogen. So this is showing in the model catalyst in UHV that it happens via a bifunctional mechanism, which is a very hard thing to prove in a working catalyst. And then we can address the ensemble effect again. This is an example. We've now gone up to 30% platinum on the surface. It forms these one-dimensional chains of platinum atoms. And what you can see straight away is that just by having a one-dimensional chain of platinum islands, not even a nanocluster or anything, just a 1D chain, you've switched off your selective conversion of butadiene to butene. And you have all this liberation of high temperature hydrogen, which means you're breaking down your molecule on the surface, forming carbon. So again, the single atom alloy is an extreme example of the ensemble effect, where the single atoms will not decompose your reactants, whereas one-dimensional chains will. So everything I've told you so far are experiments in ultra-high vacuum. I've shown you can have great atom efficiency in terms of making your catalyst. You can break linear scaling. I've shown you for hydrogen dissociation. You have a bifunctional mechanism of hydrogenation that can be very selective. So the question is, does any of this matter? Does it translate to relevant conditions in a reactor setup? And that's where my late colleague Maria Stephanopoulos and her group contributed massively to this project in demonstrating the first single atom alloy nanoparticle catalysts. This is a TEM image of a platinum copper catalyst. This is EXAFS data showing the dispersion of the platinum, that there's no platinum-platinum bonds detectable. And the strongest evidence for it being a single atom alloy catalyst is is infrared spectra of CO, where on the 1% platinum copper single atom alloy catalyst, we see only a bond. We see only a peak in the infrared spectra for COA top platinum. We don't see any bridge bound CO. So at the surface, what we have is single platinum atoms in the copper surface. And then for running a reaction, we tried again the thing we had done in ultra high vacuum butadiene hydrogenation. What you see is on a pure copper nanoparticle catalyst, the light off doesn't happen until about 100 Celsius, whereas just putting 1% platinum atoms into that copper nanoparticle drops that light off temperature by 50 Celsius. And most importantly, you keep the high selectivity towards the butane that you want because of the copper doing most of the chemistry. And this is just showing for a day on stream in an industrial gas flow where you have a lot of propane and you're trying to take out the butadiene. You see high selectivity to butane and you touch less than 1% of the propane in the feedstock. So this looks like a really promising catalytic system. Another thing we noticed during these experiments is we noticed that carbon monoxide, a common poison, binds more weakly to single atoms of platinum than to extended platinum, as you see here. So we went back to Maria's group and they tested this for the selective hydrogenation of acetylene to ethene in a flow reactor. And what they did is they compared to regular platinum nanoparticle catalysts. And when you add 200 ppm of CO, you see you lose 90% of the reactivity of the regular platinum nanoparticle catalyst, whereas you only lose half the activity of the 1% platinum catalyst because of that weaker binding of CO, that the reaction can proceed because more of the sites are not poisoned by CO as compared to platinum, which binds CO much more strongly. So that was hydrogenations. What about dehydrogenations? There's a big interest with shale gas, CH activation, and also making alkenes to go into polymers. So CH activation is rate limiting typically, and coking is a big problem because you need to use reactive elements for this. So what I'm showing here is experiments we're doing with methyl groups that we add to the surface via dissociating methyl iodide. And on a copper surface, you have to heat it up to about 450 Kelvin to break CH bonds in the methyl groups to basically make hydrogen, CH2, and then make ethene and methane. So this is basically a reporter of the temperature which CH activation happens on copper. Then we put just 1% platinum atoms into the copper surface. We do the same reaction, and what we find is CH is activated 100 Kelvin lower in temperature when you have single platinum atoms in the copper surface than on pure copper. And we can go in with the STM and we can image the reactants here, the intermediates here, where the bright spots are iodine atoms, the darker spots are methyl groups. And you can see on copper, you have to go all the way up to 450 Kelvin to activate CH and methyl, and then couple to ethene, propene, make methane, and only leave behind iodine. So it's a clean reaction. But you can see clearly here that when you have just 1% platinum atoms in the surface, your reaction's finished by 350 Kelvin. All you've got left over is the iodine atoms that came from the methyl iodide. So that's demonstrating that you can do very clean chemistry where methyl goes to ethene, propene, and methane just by adding 1% platinum to the surface. And you see we start with a half a monolayer coverage of reactants, and just 1% platinum does the job because these intermediates will diffuse around the surface, find a platinum atom, CH activate, CC couple, and give us our coupled products. So again, going to test that to see if it works under industrial conditions. So this is now taking butane, sort of shale gas analog, and running it over the 1% platinum copper single atom alloy catalyst and gas flow in the reactor. And you can see at 400 Celsius, that catalyst is stable on stream for 2 days in converting butane to butene and hydrogen. And we don't observe any coking, whereas the platinum catalyst is very active, but even after the first cycle, half an hour later, you've coked most of the sites and the activity dies off and you've covered up most of the sites. So this is a very interesting direction for CH activation, where the single platinum atom will lower that barrier significantly. But because the surface is mostly copper, you can keep your high selectivity, you don't coke, and you can also do CC coupling. And this is really nicely explained by Mikhail's group, where they plot out the energetics going from methane, methyl, CH2, CH, carbon. On platinum, that is exothermic to form carbon on platinum. So that's why platinum catalysts will coke. Whereas these single atom alloys, the red line here, will reduce the CH activation barriers, but it's exothermic, it's endothermic to coke. So you can basically go over the first step or two and then no further, which gives you the selectivity. So in the last 5 minutes of the talk, where are we going next with this? So you can imagine we've got a lot of different combinations that we could think about in this geometry. But the first thing we need to know is which combinations will likely form single atom alloy. And this is where theory work is incredibly useful right now, because the active site is so simple, you can model it very accurately on a 3x3 slab. And this is results from Mikhail's group showing that any alloys that lie above the line, this is the aggregation or the mixing enthalpy, any alloy combinations that lie above the line should be atomically dispersed, and any ones that lie beneath the line should segregate into, for example, iridium and silver areas. And one thing we use to benchmark the DFT calculations is the binding energy of CO. This is the gray bars here are the results of DFT parameterized KMC simulations for the desorption of CO. And then the diamonds here are the ones we've measured experimentally so far. So we get very good agreement for the binding of CO to these different single atom alloys as predicted with theory. Now, this is probably one of the most exciting graphs I've seen, but it doesn't quite look like it. But what this is this is both the reaction energies for a bunch of different elementary reaction steps along with their activation energies. So this is for hydrogen dissociation, CH activation, NH activation, OH activation, and CO2 reduction. So now we know for all these different combinations of metals in the single atom alloy geometry, what the activation barrier and reaction energies it is for these steps. So now if we want to design a catalyst that, for example, activates CH bonds, but not NH bonds, we can look through these tables to see for a low activation energy for CH, high for NH, and then choose that and test it. And then relevant to this meeting, a lot of these combinations will give you different scaling relationships or completely break the scaling relationships. So again, this is calculated activation energy on the y-axis, reaction energy on the x-axis for hydrogen dissociation, CH activation, NH activation, and so on. The blue lines are the linear scaling for the pure metals. The red points are for the single atom alloys. So you see in a lot of cases, you're actually lying underneath the blue line, which is good because you have lower activation energies for weak binding of intermediates. I'd encourage you to take a look at this perspective article in JPC Letters, which I borrowed the title for this presentation, for a discussion of all these different properties predicted from theory. Now, as the last 2 minutes, you know, why are these things so different? Why are we getting all these different properties from this atomic geometry? Now, it's not quite what you would sort of intuitively think, because one of the things we found from the DFT calculation is if you use beta charges and just look at the charge on, for example, a single platinum atom in copper, it predicts it has more than half an electron charge negative on the platinum and the copper versus nickel in gold, which has a deficiency of 0.3 of an electron. And this is basically because you're putting unsimilar elements together, which have different ionization, electron affinities, and so on. And you do get charge transfer between them. So even though you'd think of this typically as it's an alloy, the electrons are smeared everywhere, it's neutral. The old view of alloys is that you put elements in, you subtly shift the D band to get properties you want. This is quite different because you don't have this mean field view of the surface. It's actually quite localized where you have charges on these atoms. And then most recently, this is something John Kitchen calculated years ago, is that you have these free atom-like states of the single atom alloy. So this is a recent paper from Robert Schlogel's group looking at copper atoms in a silver host. And what you can see from the synchrotron XPS is that this is the D band of the silver host, whereas you put a single copper atom in, you have a localized copper state. There's very little hybridization of the copper atom with the silver host, which means the electronic structure of this copper atom looks much more like a copper atom in a vacuum than it does a copper in a copper metal. So it's because of the lack of hybridization between a lot of these combinations, you get these localized D states, and that's where a lot of the reaction can be centered, and that sort of breaks you away from typical the D-band model and so on. And I'll point you towards a fairly recent paper by John's group that discusses a lot of these computed electronic structures and the effect on reaction barriers. So I'll leave the conclusions up when I finish, but just to thank the people that did the work. Again, this has been about 12 years of experimental work from my group here, from Maria Stephanopoulos' group, from Mikhail's group in London. And I'd really like to thank the Department of Energy for years through a CPIMS grant to really do the fundamental surface science to develop these things, and then a joint grant through the catalysis program I shared with Maria Stephanopoulos to realize a lot of these systems in more industrially relevant conditions. And thanks for your attention on this call.
All right, thank you very much, Charlie, for an excellent talk. We've got quite a few questions. We'll try to get through a couple of them before our break. And then as always, we'll be posting these to a Google Doc. So a few of the questions have been along the lines of the agglomeration of these single atom alloys or their stability. And so if you could comment on what you've seen with that.
Yeah, to reiterate, a lot of these combinations I'm showing here, thermodynamics drives the atomic dispersion, because if your aggregation energy is positive, your tendency is to isolate palladium atoms in a gold surface is more stable than a cluster of palladium atoms. So for a lot of these metal combinations, it's just the mixing thermodynamics that gives you the atomic dispersion, where a lot of these combinations work, but not, for example, iridium silver would be a bad choice. Now, in terms of stability, the thermodynamics keeps it well isolated, but then in terms of a reaction, you're going to have reactants on the surface, and that's what stabilizes the atoms in the surface, whereas if you flow hydrogen or helium, they may disappear into the bulk. So it's really the reactions, intermediates on the surface are stabilizing those single atoms in the surface layer and allowing the catalysis to proceed.
Another related question, I'm trying to merge a couple of the ones here. There's been some interest about how much loading can you have of these single atom alloys as a maximum, and under catalytic conditions, how much of those would you expect to be subsurface?
Good question, and it's a tough question because of what I just mentioned, is that depending on the partial pressures in the gas phase over the catalyst, that will dictate under steady state what the population of atoms in the surface. So every different reaction will have a different percentage population of those single atoms in the surface versus the bulk. But you can play tricks like you play in regular catalysis. You can make small particles that you have more surface area per bulk. That's a way to up the active site number. But I'd say it depends on the reaction you're trying to run. In terms of stability, we've seen other people in the field run these catalysts up to over 500 Celsius, and they're still atomically dispersed. The only stability issue we have right now is just sintering of the host metal itself. For example, copper and silver and gold are very liable to sintering. So the activity shuts down, not when the single atoms disappear, they're always there due to thermodynamics. It's when the particle sinters and loses surface area. So that's why we're looking into things like atomic layer deposition to stabilize the host metal itself and then keep this chemistry even hotter in temperature.
All right, well, thank you again, Charlie, for an excellent talk. We'll be getting the rest of these questions to you, and then we'll post them on the Google Doc for everybody to see the answers to them eventually.
Thank you.
Thank you. All right, so now we're gonna take a brief coffee, tea, or whatever your poison is break until about 2 p.m. when we'll have Karen Chan up next. All right, so we're back from our short break, and up next we have Professor Karen Chan. She's an associate professor from Technical University of Denmark in the physics department, and she's going to be talking to us about surface charge densities and what that's going to mean for all the energetics of electrochemical reactions. So Karen, it's all yours.
Okay, thank you, Omar. Can you hear me?
Yes.
Okay, great. All right. So first of all, thank you, Omar, Zach, and John for organizing this virtual symposium. It's great that we can still share given all the restrictions we have on travel. And so as Omar said, I'll be talking primarily about surface charge density as opposed to the work function as the appropriate descriptor of the driving force for electrochemical reactions, what this means about how we calculate barriers, and just a peek at what it means for electrochemical CO2 reduction. And so before I get started, I want to acknowledge the people who did all the work. And so shown in the pictures here are the first authors or the co-first authors of the work. And so Joe Gautier did the methods to model electrochemical barriers. Stefan Renge worked on electrochemical reduction of CO2 on gold, as well as ion effects. Sudarshan here is working on single atom catalysts. Carlos used to be a part of Tom Jaramillo and Chris Hahn's group, and he worked on electrochemical CO2 reduction on gold. And Ezra, who used to be in Alex Bell's group, did the experiments of ion effects in the electrochemical CO2 reduction. So I also would like to thank the co-authors of the work that are shown here, who also contributed, as well as the PIs who drove a lot of the efforts behind the works that I'm going to show. So I want to first start with the model system that we would like to understand. The electrochemical interface, as we know, is rather complex. There is always the presence of a solvent, which can have increasing ordering as we approach the interface. At the surface, there are adsorbates and the reaction intermediates that we are interested in. There is a charge separation where the countercharge is distributed in solution in various ways, and this charge separation sets up the potential and field at the interface, which drives the processes that we are interested in. And finally, the resultant kinetics are often coupled to mass transport processes, which convolutes the activity response to an applied potential. And so when we're talking about the driving force for electrochemical reaction, I want to start out with a perhaps simple and classical view of the potential drop at the interface, where we have here a rather linear drop across a compact layer and a diffuse layer corresponding to the distributed ions in solution. And when we are talking about the applied electrode potential, we are generally talking about the metal potential relative to some bulk solution potential, as we can see here, okay? It's also possible in experiments to report it relative to a reference electrode, but that's essentially equivalent because there is basically a constant offset between the bulk solution potential and the reference potential. But when it comes to what's really driving our electrochemical reactions, it's really this local potential drop, as illustrated here, that is relevant, okay? And so the metal potential relative to some potential at the reaction plane. And this is not uniquely determined by the applied electrode potential, because one can envision with perhaps a different ion concentration, we can have a different driving force, as I've shown here. And so this really is the idea behind the Frumkin correction to Butler-Volmer kinetics, which is decades old. And this local potential shown here is basically proportional to the interfacial electric field, which then through Gauss's law is related to the surface charge density. And what I will suggest here is that this is a more appropriate descriptor of the driving force in electrochemical reactions. It influences how we calculate electrochemical barriers, and it also presents some opportunities for catalyst design. Okay, so then starting out with barriers then. So when it comes to calculating electrochemical barriers and really any process where there is a dipole change along the reaction pathway, one of the major challenges in the field is how we can determine the kinetics under a constant driving force, because a simple explicit or fully explicit solvent simulation, we are looking at a constant number of electrons, whereas in experiments, we are operating under constant potential. And this challenge here is illustrated by the simulation of a Hayrovsky reaction, which is a proton-electron transfer to an adsorbed hydrogen. And what these charge density isosurfaces show us is that there's a significant shift in force along the pathway. This we can also see in the work function corresponding to this, where for this very typical simulation, we get a change of 2 to 3 volts along the reaction pathway. And this is well beyond the potential range of any process that we would be interested in. And so in the past decade or so, there's been a number of mitigation strategies that have and I'll go over them briefly here. One of them, I'll call this cell extrapolation. And what this is at larger cells, the change in charge density along the reaction pathway is significantly smaller. And so the idea then would be to do the calculation in a series of larger and larger unit cells until we can extrapolate to the infinite cell size limit, where then the potential is constant along the reaction pathway. And so this is computationally quite heavy. And an alternative to this, and I'll call this the charge extrapolation scheme, whereby relying on a capacitor model of the interface, if we can partition the charge at the interface, we can relate the small cell size result to the infinite cell size limit. The issue here is that we face some challenges with charge partitioning for certain reactions, and so this isn't completely general either. One alternative that has been increasingly popular in the past few years has been the use of implicit electrolytes. And how it works is upon a reaction process that leads to a significant shift in dipole, for instance, CO2 adsorption, one simultaneously applies a continuum charge, for instance, like so, such that the driving force for the reaction remains constant along the reaction pathway. And there's a number of different ways to apply a continuum electrolyte. One of them is a linearized Poisson-Boltzmann approach. And just as example here, this is a corresponding charge density isosurface associated with that. And so because of the multitude of possibilities in how we change the driving force at the electrochemical interface, my group in the past year or two have looked at developing a sort of general framework for us to determine reaction barriers from both implicit and explicit electrolyte models. And this model considers the various possible charging elements at the interface, whether it's an explicit charge like this, charge coming from coadsorbates, or charge coming from continuum approximations, and there's a number of different ways we can do this. We consider each of them to have their own capacitance, and so it sees the interface as a combination of different capacitances corresponding to all these different elements. And a critical aspect of this approach is going back to the title of this talk, that it's the effective surface charge and not the work function, which is the more appropriate descriptor of the driving force for activity. And this idea is best illustrated with an example. Okay, and so let us consider the Volmer reaction as an example here. And so this is basically a proton-electron transfer to the surface to form adsorbed hydrogen. And in the case that we are working only with explicit electrolyte, the only way that we can change the driving force for this process is to change the ion concentration. And practically what it means is it means doing our calculations in different cell sizes. And so shown here is exactly what we have done. This is the Volmer reaction energy as a function of work function calculated at different ion concentrations using fully explicit solvent. It's also possible to change the driving force here by adding some implicit charge, for instance, using a linearized Poisson-Boltzmann model, like so, for instance. And so what we find is that when we do that, we essentially get high-valued functions for the energy as a function of work function, depending on the cell size in our simulations. And so in this case, the work function does not uniquely determine the energetics when there's multiple charging components with different capacitances. And what this also suggests is that some existing results could also be different if they were redone in significantly different cell sizes. And this really makes sense going back to this kind of Frumkin picture of the interface where the driving force for a given reaction is not uniquely determined by the applied electrode potential, and that this driving force is basically proportional to the surface charge density. And indeed, if we were to re-examine the previous set of data as a function of surface charge density, then we indeed get a single valued function. What this also means then is that the energetics that we determine as a function of surface charge is also insensitive to the type of countercharge model that we apply, whether it's explicit charge, planar, Poisson-Boltzmann, and so forth. And so my suggestion in terms of calculating electrochemical barriers is that instead of calculating them as a function of work function, we look at them as a function of surface charge, and we can relate them to functions of potential using known charging properties of the interface, such as the double layer capacitance, as well as the potential of zero charge. And this is the approach that we have taken in order to do a mechanistic analysis of CO2 reduction. Okay, and so I'll just talk very briefly about some latest results, first focusing on the importance of field effects. Okay, and so what makes CO2 reduction special relative to some other popular reactions is its sensitivity to the interfacial electric field. And so shown here is the adsorption energies for a number of important CO2 reduction intermediates as a function of electric field. And essentially what we find is that the adsorbates that are most sensitive to the interfacial field are the ones with vertical CO bonds. Such as CO2, OCCO, and OCCHO. And this has important impact on its mechanism, as well as how pH and ions affect their overall activity. And so as an example, we can look at CO2 reduction on gold. And shown here is the result of a joint theoretical experimental study, where shown here is the experimental data along with a whole bunch of other experimental studies for basically the current response to an applied voltage. And what we find in our kinetic model is that it is actually the CO2 adsorption step, which generally limits the activity over the potential range that we are interested in. And as a result, then the Tafel slope for this reaction is proportional to the dipole of the CO2, which interacts with the electric field, as well as the double layer charging capacitance. And the activity is affected by the field, which is proportional to the charge, which then is also affected by the charging properties, the double layer capacitance, and the potential of zero charge as well. And what this suggests is that in addition to the energetics, we can also tune the double layer charging properties towards better activity. And this is exactly what ions do. So it's been shown experimentally that CO2 reduction is highly sensitive to the cation composition, where between lithium and cesium in the electrolyte, there can be between 1 to 3 orders of magnitude difference in activity towards some of the products that we are interested in. And our hypothesis here is that it really is a size effect, whereby lithium with a larger hydrated radius than cesium can fit fewer ions at the interface at a given potential. And this really translates to a different surface charge for cesium as opposed to lithium at a fixed potential. And it is this difference in surface charge that gives the enhancement in activity that we see. And this is something that we can model quite easily by combining a continuum modified Poisson-Boltzmann model of the ion distribution with our ab initio reaction energetics computed as a function of surface charge. And so shown here is the comparison between the theoretical prediction and the experimentally observed differences in activity, which are shown in dots, and the theory is shown in lines. And so here, what we're showing here is the difference between lithium, sodium, and cesium, and so forth for C2 products produced on copper. And here is the CO production rates on silver as a function of different ions. And we can see that the agreement is very reasonable. And we can do the exact same analysis with the vibrational stark shifts as well at different electrolyte composition. And again, the agreement is very reasonable. And what we can take away from this very simple analysis is that small hydrated cation radii, and actually in principle, large charges, if they can be stabilized in solution, are advantageous towards various interesting products in CO2 reduction. And the last point I want to bring up is that in addition to tuning the double layer charging properties, we can also tune the activities through the adsorbate dipoles, and this can be done using single atom catalysts. And so very recently, we've been very interested in iron, nitrogen, carbon catalysts simply because they have shown such promising geometric current densities when put into a gas diffusion electrode. And these catalysts have the same mechanism as on gold for CO2 reduction to CO. But what is special about them is that they are able to localize charge a little differently, such that they have different dipoles upon adsorption. And this is shown here in the transition state for CO2 adsorption as a function of surface charge density, where with different site motifs, we get different slopes, which reflect differences in their adsorbate dipole. And when we're comparing then the simulated kinetics with experiments, what is suggested by our analysis then is that this new iron, nitrogen, carbon catalyst from Zile Hu's group, which has a very steep Tafel slope, should correspond to a different active site. And what this also suggests is that we can, in addition to binding energies, tune the adsorbate dipoles towards higher activity. Okay, and so with that, these are the main takeaways from this presentation. Number one, that we should be looking at surface charge density as opposed to the work function as the driving force for electrochemical processes. And with this approach, we can basically understand new descriptors for CO2 reduction activities beyond binding energies. So the interfacial charging properties such as the PZZ and the double layer capacitance, and the ion size effect is really there through changing the double layer capacitance associated with a given interface. And in addition to that, it is possible that we tune adsorbate dipoles towards higher activity as well, for example, on single atom catalysts. Okay. And so that's it. Any questions?
All right, thank you very much, Karen. We've got time for a couple of quick questions. One of them is about true driving force that you were showing in your slides, and whether that should be the electrostatic potential of the ion as an adsorbate versus what it is in free solution.
Sorry, can you repeat the question? I can't quite hear you.
Sure.
Hello.
So
Sorry.
the question is about the true driving force.
Yes.
And say, shouldn't the driving force be the electrostatic potential of the ion as an adsorbate versus in free solution?
I would say the true driving force is basically the potential difference between the metal and basically the potential at the reaction plane. So all I'm saying is that we shouldn't be looking at the bulk potential. We should be looking at the potential where the reaction occurs. So
Okay.
whatever the electron would experience, yeah, where it is transferred.
Got it. Another question is about in your formalism, would it be more appropriate to use the potential of zero total charge instead of the point of zero charge?
It would not be the potential of zero total charge because that would include the charge transfer due to adsorption. It would be the potential of zero free charge if it can be determined without the interference from adsorption.
Okay, well, in the interest of time, I'll be posting the rest of these questions to the Google Doc, and thank you again, Karen.
Thank you.
All right, so we've got our next speaker, Ditya Savara, if you're there and if you can share your screen. Okay, great. So our next speaker is Ditya Savara from Oak Ridge National Lab. And he's going to be talking to us about kinetic parameter estimation using Bayesian parameter estimation. So Ditya, if you're there, please go ahead.
Thank you. Can you hear me okay?
Maybe if you could get closer to the mic a little bit.
Okay, is this better?
Yes, thank you.
Okay, great. I'm excited to have this opportunity today to present to you a vision of the future in which Checky-Poo is used for Bayesian parameter estimation. I've been working with Eric Walker on developing this software, and hopefully by the end of this presentation, you will see where Bayesian parameter estimation might be useful in your own research. I'll talk about the big picture, some general information about parameter estimation, a little bit about Checky-Poo, and Bayesian design experiments with a single slide at the end. So the big picture, at least for me, is looking at experiments and calculations for more accurate predictions. We're interested in activation energies, mechanisms, etc. We have guesses from previous experiments, density functional theory, linear descriptors, and other sources of knowledge. This prior knowledge has uncertainties, and there's an excellent focus in research right now of trying to minimize those uncertainties as much as possible. However, even those uncertainties themselves are valuable. And so what I'm going to argue in this talk today is that we should be using those uncertainties, taking experimental data and their uncertainties, and computational data and their uncertainties, using them together to get the most physically accurate values. We'll be doing that with kinetic modeling, that is kinetic simulations, and Bayesian parameter estimation. So a simple example of parameter estimation using experiment and simulation together. This is a temperature programmed reaction experiment we're looking at here. And for those who are not familiar, we start with an adsorbate on a surface. We heat up the surface at a controlled ramped rate. So this axis is also time. Initially, molecules desorb. There's a maximum in rate for desorption because as molecules desorb, they're depleted. The rate goes back down. And that's a result of molecules being depleted until there are no molecules left. It's common in the literature to use kinetic simulations, varying the kinetic parameters, in this case, activation energies and pre-exponentials, to achieve as good of a fit as possible. But what happens when those fits are not physically realistic? What if density functional theory or other electronic structure calculations, sorry, is there a chat thing I need to pay attention to? Is there still a difficulty in hearing me? This is at...
Yeah, maybe if you can get a little closer to your mic again.
Okay, is this a difference again?
Yes, that's great.
Okay. So what happens when those estimates are not realistic? We can have different sources of knowledge, including density function theory, electronic structure methods, as well as other sources of chemical knowledge I do want to point out that it's not only electronic structural calculations. There are also cases where, for example, you can have experiments that provide a Bronsted-Evans-Polanyi or Bell-Evans-Polanyi relationship, and that still has values and uncertainties. So what happens when we have an estimate from fitting that is not realistic, because maybe our prior knowledge tells us it should be closer to 40 kilojoules per mole, but the fitting might say it's 10 kilojoules per mole. What do we do in this situation? Should we penalize the unrealistic fitting? And if so, by how much? My answer to that question is that we should not try to penalize the fit. We should change the question. With Bayesian parameter estimation, we change the question from what is the best fit to what is the most physically probable set of values. And this question has a well-defined solution. I don't want to go into the nuances of Bayes' theorem for the audience today. What I would like people to take away from this talk is there are two terms on the right. One of them is associated with the values of the observed data and the uncertainties. The other term here is associated with our prior knowledge, typically from density functional theory, and the uncertainties. On the left-hand side, we have our values that we're interested in estimating, specific values such as an activation energy, and we try to find them, at least in this talk, we look for the maximum probability. I want to draw this distinction that we are intentionally using the word estimation rather than optimization to emphasize that we're not trying to find the best fit, but the most physically realistic values. Now to look at a specific case, here's a case with ethanol desorption from serum oxide. As before, there's a peak. We have a maximum around 220 Kelvin in this case. And this particular peak is too broad to be described by a single first order reaction with a single activation energy. That means we can either look at more complex models with multiple states, multiple sites. We can also look at models where you simply have a dependence of coverage, dependence of the activation energy with coverage. I'm not going to show it to you, but I will tell you that if you use a single activation energy with a linear coverage dependence, you still cannot produce this peak. Now we're going to look at first a case with two states on the same type of site, where each state has a linearly coverage dependent activation energy. And the equations are not important for this talk. What's important here is you have some parameters and you get a rate. And we're going to compare CPE, conventional parameter estimation, and Bayesian parameter estimation. In this case, we have two activation energies and two pre-exponentials for this particular model. So first, we do a conventional parameter estimation where we try to minimize the weighted sum of squared residuals, weighted by the uncertainties in this case. And we do get a very nice fit. So we can call this a successful application of conventional parameter estimation. When we compare this to the Bayesian parameter estimation, we start with the physical knowledge of, in this case, 40 kilojoules per mole with some uncertainty for the adsorption strength of ethanol and serum oxide. We have our estimate of the pre-exponential ahead of time with some uncertainty, and we seek to find the maximum of the posterior distribution. And this is the output, which is a reasonable reproduction of the main peak. And this tail is at least in reasonable agreement, let's say, with having a shoulder like this. When we compare the two of them, you might ask the question, why do we use BPE if we get a worse fit? And what I'm going to show you here is indeed the main point I'm trying to make in this talk, is that the BPE result and the CPE result for state one both have physically realistic results as relative to our prior expectations of where physically realistic results may lie. But for adsorbate state two, the BPE result does give a data point which is in close agreement to the prior, while the CPE result is totally unrealistic. We have a pre-exponential that is beneath 1. This is a log scale. And we have a activation energy that's beneath 10 kilojoules per mole, maybe even beneath 5 kilojoules per mole. Well, this should be joules. There's a misprint here in the axis. So the BPE values are more realistic than the CPE values. And now let's go to a more complex case. We can try to add in not simply linear activation energies. Previously, we had a constant in this gamma. So there was a linear dependence with coverage. Now we'll allow this gamma to vary as well, still in a monotonic fashion, so that we don't have a strictly linear dependence. Real adsorbate coverages are not simply linear. And by doing so, we can actually have enough flexibility to produce that peak shape with a single species at a single site. The conventional parameter estimation result, again, has a very successful reproduction of the peak. The BPE map is actually a better match than previously, now that we have more flexibility in this gamma term. But once again, the CPE result is physically unrealistic. This is too low of an activation energy, and the pre-exponential in particular is quite low as well. Whereas the BPE result has a realistic activation energy and a realistic pre-exponential. One thing that greatly surprised me in this example is that both graphs, but in particular the BPE graph, requires a coverage dependence of less than 5 kilojoules per mole across the experiment. And the key thing, though, is that you did require a beyond linear coverage dependence for this result. We can look at the shape of the posterior. This is for the initial coverage of the reaction's activation energy. And we see that there is a defined shape. It's within a realistic area for the prior. And we can also get correlations between the activation energy and the pre-exponential. One thing I should make a point of is that all 3 of these figures came out of the Checky-Poo software. So these types of figures are produced automatically, as are these, as are the simulation results. So for this vision of the future, complexity is good and not bad. As shown in that example, we needed to have this non-linear dependence. And this is actually where the real strength of BPE comes in. Why? Because BPE seeks the most realistic solution from all solutions. So it's ideally suited for cases that would normally be classified as overfitting. Now comes an important question, which was asked about by one of the viewers in the earlier noted perspective article, which is, how do people perform BPE? Because people don't normally have the training for it. And to answer that question, this Checky-Poo software is being developed. We're going to have a tutorial for it that we're going to release as well. And it will be very close to plug and play. So the idea here is that we simply have to define our experimental data along with the uncertainties. We can build kinetic models. You can use a CSV file or Python. We already have a Cantera interface. I'd love to see an interface to the PyMut kind of software and other ones. It's actually quite general software. It's not limited to chemical kinetics, although that is, of course, what we're using it for at the moment. You have to define your priors as well, which in this context is going to be your typically density functional theory estimates, but it can be from other relations, etc. The uncertainties associated with them. And I should emphasize again that we do want to encourage complex problems because that's where BPE works well. And larger data sets that exist today in the literature and are being developed will give meaningful priors to put into that previous step. Finally, we do the simulations. We get posteriors out of the software. Right, and that's the whole process in a nutshell. So the intent here is that users don't need to understand what's going on under the hood. They don't need to understand the equations, and that's true for the following slides as well, that we can do things that go beyond parameter estimation. One of the things is design of experiments, and another is model discrimination. I'm not going to spend too much time on this slide, but the key point here is that if you have a particular set of parameters you're interested in, such as a difference in energetics between two states or an activation energy, et cetera, with Bayesian parameter estimation and design of experiments, you can actually assess what conditions are best to perform your experiment to get the most information. So in this simple example, which we'll put into our publication that's going to be forthcoming, that for these two temperatures, the 298 Kelvin temperature would be the better temperature to perform the experiment at, because the distribution of the posterior in red is narrower, which means you get a more accurate, or sorry, more precise, actually, the same accuracy, but the more precise estimate, at least in this example, a more precise estimate of your parameter. In addition to design of experiments, there's also model discrimination. If you have two different models, such as two different reaction site types, or even two different mechanistic possibilities, and one is unsure as to which one is more physically probable, Bayesian model discrimination, also built in here, is going to be able to tell you for two different models which one is more physically probable. And one thing that I should make a small note of is that it's not always the model that produces a data point that's closer to experiment. That's not always the most physically probable. It's sort of like the same concept as the conventional parameter estimation, where the closest fit's not always the most physically realistic one. Sometimes you're getting a better fit at, or better match at the expense of physical realisticness. So in summary, this software is one we're developing. We're quite excited about it. This was, at least my half of it, was sponsored by the Department of Energy. And with that, I will be happy to answer any questions.
All right, thank you very much, Aditya. We do have a few questions. We'll try to get through as many of them as possible. So the first question says that many times the reaction conditions are not properly controlled. Example, Reynolds number, temperature measurements, and several publications are made without control on these variables. How to discount this during the analysis?
You raised a great question, actually. And actually, this is a really appropriate question. So one thing that Andreas Heiden has made a big point of is that experimentalists are much less conditioned than computationalists to report the uncertainties. And one thing that would be very useful is if more uncertainties are reported in the literature. That being said, with sufficient knowledge, perhaps we can estimate the uncertainties in experimental data sets. And it's also good to know that you don't have to be exact about it. In Bayesian parameter estimation, as long as you have a reasonable estimate of the uncertainty, you want to go higher rather than lower, you can still perform the analysis. So that's a great question. One of the advantages is we can just analyze previous data sets with reasonable estimates of the uncertainty.
Got it. Another question asks, in conventional parameter estimation, you rely on the physical constraints that are clearly defined. But in this BPS, you're making a difference between 13 and 23 kilojoules per mole. One is right, the other is not. What is the basis to define these limits?
Another good question. One thing I want to note is that when you look at the Bayes theorem, this term, which is the likelihood, does correspond very much to the same things that you are optimizing in conventional parameter estimation. The second term related to the prior defines essentially, not with hard limits, right? These are not hard limits, but it does have a effect on the probability of what's most physically realistic. In this case, often from DFT. So you have a distribution of what you expect, and it's not a hard limit, generally speaking, but it is a distribution.
Okay, and I'll try to combine two more questions while I start prepping the next speaker to share their screen. It seems that BEP is dependent on parameters that you consider to be physically realistic. Does this presume that your prior knowledge of the system supersedes the result from your model fitting? How would that work for unknown or complex systems? And the other question I think you'll be interested in answering is, when will this software be available on GitHub?
Right. Because if you go to that link, it doesn't show it to you yet. It's private right now. Let me answer that one first and then come back if there's time. We are in the process of making a publication. And again, by mid-2020, we hope to make it public. I'm willing to collaborate even earlier than that. We do want to, and I should have made this point more strongly, we would really like others in the community to contribute to this software as well. Not just potentially in advance, but more importantly, once it's public, because that will simply make it a more strong package. And we are all for that. The other question, just to answer it very succinctly, given the time constraints, it is very important to have priors. You must have guesses. When your priors result in a ill matching result, that's actually a sign that the model is a bad model. So you get information even in those cases. I'm sure we're out of time now, but thank you for those questions.
All right, thank you very much again, Aditya. I definitely look forward to your software becoming publicly available. So if our next speaker is here, you can go ahead and start sharing your screen. All right.
Could you hear me?
Yes, I can hear you. Maybe if you can get a little closer to your microphone.
Okay, could you hear me now?
Perfect. Okay, so our next and our last speaker for the session today, but don't leave yet after that, we have some questions we have for you, is Zongtian Mao from Charlie Campbell's group at the University of Washington. And they've got some cool work on their new insights on their degree of rate control analysis. So Zongtian, it's all yours.
Thank you. I would like to share some recent work we did on the degree of rate control analysis. So the rate determinant step or rate limiting step is a central concept in the chemical kinetics, but the definition of the rate limiting step is usually not clear. People may say it is the bottleneck of the reaction mechanism with the smallest forward rate constant, or people may say it is the step with the highest energy of transition state. The original purpose of degree of rate control, DRC, is to strictly define which step is rate limiting. The definition is a partial derivative of logarithm of the rate with respect to the logarithm of the forward rate constant of step I. Keep the equilibrium constant and all other rate constants constant. An easier equivalent description can be the partial derivative with respect to the negative Gibbs free energy of the transition state in step I over RT, keep all other Gibbs free energy constant. It is if you change the energy of a transition state in a reaction mechanism, how much the overall rate will change with this energy change. With the DRC analysis, you can easily define which step is rate limiting because in a rate limited step, the DRC equals 1. If we use the definition based on the Gibbs free energy, we can easily extend the application of the DRC from the transition state to any other species in the reaction, like the intermediates, the products, or the reactants. So this generalized DRC tells you if you change the Gibbs free energies of one species in a reaction, how much the overall rate will answer to this energy change. In some of my following slides, I will use this small reduced G instead of the negative capital G over RT. So using degree of rate control analysis, you can simplify a very complicated reaction mechanism into a few species with non-zero DRCs. And these species, we call them the rate controlling species. You may think the DRC is just a mathematical concept, but in fact, they are closely related to the experimentally accessible data. Or you can say you can measure the DRC in experiments. This is an example. It's a carboxyl reaction mechanism in water-gas shift reaction with 8 elementary steps. As I mentioned, the DRC of the rate limiting step is 1. In the real world, the activation energy of step 5 here is 0.47 EV. In this case, step 6 is the rate limiting step. So you can see the DRC of step 6 is 1. But if I manually increase the activation energy of step 5 in the calculation, you can see the DRC of step 5 increase and the DRC of step 6 decrease. Until you have a high enough activation energy for step 5, it takes over as the rate determinant step. Then step 6 goes down to 0. In experiment, you can use many methods to determine the rate limited step, and you see the transition state in the rate limited step has a DRC of 1. The other part is about the DRC for the catalyst-bound intermediates. Their DRCs are proportional to their fractional coverage, theta, and the proportional factor, sigma, equals a summation over all steps. The xk here is the DRC of step k. Nk is the number of sites that participate in the step. For example, if we are here, step 6 is the rate limiting step. Then we see 2 sites in step 6. So this factor equals 2. For CO adsorbate, its DRC equals -2 times its fractional coverage, about -1.9. If we are here, it's step 5, take the rate limiting step. Then this number equals 1. So for CO adsorbate, it equals -1 times its fractional coverage, about -1 for its DRC. This is a simple example for DRC analysis, the Langmuir-Hinshelwood mechanism. If we assume step 3 is virtually irreversible and A star is the most abundant surface species, this is the rate equation. You can easily calculate the DRCs for species in the reaction mechanism. Transition state 3 has a DRC of 1. It means step 3 is the rate determining step. For adsorbate A, it has a DRC of -2, which equals -2 times its fractional coverage, about 1. For all other species, they have DRCs close to 0. And after we know the basic properties and basic rules of DRC analysis, here is the first application for computational catalyst screening. This is the energy diagram of the methane steam reforming on rhodium and ruthenium catalyst. If you change the catalyst from rhodium to ruthenium, you can see the energy of species change and the rate will change. This is exactly what DRC want to tell you, how much the rate will change if you change the energy of species. So we start from the definition, it's a partial derivative. So we can reorganize the definition as and rewrite as a total differential like this. And then we can integral from the reference catalyst, which is rhodium here, to the energy of the new catalyst of interest, which is ruthenium here. And this is the equation. You can use the equation to calculate the relative rate with respect to the reference catalyst using the degree of rate control of species. However, it's usually not easy to conduct integral in the research. So we further assume the DRCs are independent of the catalyst material in a range of interest. And this is the final version of the equation. You can see if we know the degree of rate control of species with the reference catalyst, and we know the energy change from one catalyst to the other one, we can calculate the relative rate from one catalyst to the other one. Remember, only a few species has non-zero DRCs. So only these species contribute to the summation here. Once we have the DRCs on the reference catalyst and we know the energy of species on the catalyst, we can calculate the energies of only the rate controlling species on a new catalyst and use this equation to calculate or estimate the relative rates on the new catalyst. Here is the result. In the DRC method, we search the catalyst in a space formed with the energies of the rate controlling species. For example, here, they are the adsorbate CO and the transition state CO. Each catalyst of interest have a position in this DRC map. If we only consider the first two rate controlling species with the largest DRC, these two species, we can estimate the relative rate relative to the reference catalyst using this equation. We can see the relative rate estimated using the DRC method is very close to the number estimated from the actual DFT calculation. Remember, when we derive the equation, we assume the DRC is independent of catalyst material. However, this assumption is not always true. If you look at this DRC map in the Noskov-Bligard descriptor space, you can see in large regions, the dominant DRC species does not change. It's okay. But if you move the system from one side across the boundary to the other side, the DRCs can change rapidly, and this assumption does not hold. If, like from rhodium to ruthenium, the DRC of carbon can change a lot. If you include the carbon into the estimation, it can cause more error than just use the two simple, most rate controlling species. To summarize, in the DRC method, we establish the reaction mechanism on a reference catalyst, for example, rhodium, and then calculate the DRCs to find the rate controlling species. And remember, you can also determine the DRCs in experiments. Then we go to a new catalyst, calculate the rate, first calculate the rate controlling species energy with accurate method, and then estimate the rate on the new catalyst. So our key strategy is to reduce the reaction mechanism to a few rate controlling species, and this allows us to treat them more accurately. For comparison, the Noskov-Bligard method calculates the energy of species on several typical catalysts first and establish the linear scaling relationship. Then they obtain the new energies of species on a new catalyst using this linear scaling relationship. But this step can sacrifice some accuracy. For example, the binding energy of Cl in uranium from linear scaling can be about 0.5 eV higher than the actual DFT calculation. And then they calculate the rate using the not that accurate estimated energies using microkinetic model. So their strategy is they reduce the work for calculating the energies for all species by estimating them with a few descriptors. For us, it's a few rate controlling species. Another application is about kinetic isotope effect, KIE. This is the reaction of CO2 hydrogenation on copper. If you use hydrogen, the energy diagram is the red one. If you replace hydrogen with deuterium, you can see the energy will change and the energy diagram will be the blue one. The rate will also change. The logic is the same as the catalyst screening method. The only difference is now it's the relative rate from hydrogen isotope to deuterium isotope. I summarized the DRCs and coverage of species in the reaction. First, looking at these two columns, from hydrogen to deuterium, DRCs does not change much, so the assumption is solid here. Also, there is only a few species contribute to the KIE. Plugging the number of these three species into the equation gives RH over RD equals 0.4, an inverse KIE. The full microkinetic model gives 0.45, very close to the number from DRC analysis. It's interesting here because people usually think the rate determinant step determines the kinetic isotope effect. But here you can see this is the transition state in the rate determinant step. But hydrogen format, they're not, but they contribute to the KIE. Acetic acid is in the rate determinant step, but it has no effect on the KIE based on the DRC analysis. After I finished this project, a question came into my mind. It is, in textbook, you can see the KIE is a result of the isotope substitution. It changed the 0 point energy and changed the activation energy, and thus changed the rate. Since we proved that for a multi-step reaction, you can calculate the KIE using degree of rate control, then my question is, can I express the apparent activation energy for a multi-step reaction using the degree of rate control analysis? And the answer is yes. I will not show the detailed derivation here, but just the final result. E apparent of a multi-step reaction equals RT plus a summation over all species in the reaction mechanism. This summation is actually an averaged enthalpies of species weighted by their DRCs. And since only a few species has non-zero DRCs, only a few terms in this summation are effective. Let's start from something simple, a Langmuir-Hinshelwood mechanism. From the same equation, we can easily calculate E apparent equals RT plus the energy of transition state 3 minus 2 times the energy of adsorbate A. If we use our equation, this one, and plug the DRCs into this equation, we actually get the same result as the actual value. Another method for apparent activation energy is the energy span model from Kozuk and Scheik. They said the apparent activation energy is the highest energy span in the reaction energy diagram, which is transition stage 3 minus A star minus B star in this case, but this is not correct. Usually the energy span model doesn't work for surface reactions. To show how it works for a more complex reaction, we use the hydrogenation reaction we studied before. If we use the reactants as the 0 point for the energy, then only 2 species has DRC, non-zero DRC and non-zero enthalpies. For comparison, I calculated the energies using the rate with a microkinetic model in a range of temperature. The Arrhenius plot gives E apparent equals 209.78 kilojoules per mole. In this table, I have the DRCs and the enthalpies of species. We can plug all these species into this equation. It gives 210. But this is not necessary. You can just plug these 2 species into the equation. It gives almost the same result. And both of these 2 numbers are very close to the number from the Arrhenius plot. Here are the new equations I mentioned in my slides, the 2 similar equations for catalyst screening and kinetic isotope effect. This one is the equation that relates the DRC of intermediates with their fractional coverage. And this is the apparent activation energy result. I would like to thank Professor Campbell and group members in Campbell Lab. I thank my advisor, Charlie Campbell, for giving me this chance. And also thank DOE for supporting this project. And thank you for your time.
All right, thank you, Zongtian. Thank you for a very nice talk and that information about degree of rate control. So we've got a couple of questions and we have some time for more if any come in. The first question is there any reason that total DRC is 1?
For a simple reaction, James Domestic proved an idea. But if you want a general proof, it is like for each step in the reaction, there is a KBT over H times some function of the concentration distribution under reaction condition. The total DRC sum up to 1 only for transition state. You can assume if you increase the energy of all species, all transition state in the reaction mechanism, it is equivalent to if you put the reaction in a world with a higher frequency, everything there is faster or slower. If you put the factor, the same factor for all transition state on this factor, you plug it into the equation, you can get it add up to 1. But it's always true, it's solid.
All right, and another question asks, why does the energy span model not work for surface reactions?
So this is a very good question. So for energy span model, they start this model for organic chemistry. The basic difference between organic chemistry catalyst and surface catalyst is usually in organic chemistry, they have only one catalyst site. It can be a homogeneous catalyst or enzyme. So their energy span model states it's the apparent activation energy. The apparent activation energy equals the highest transition state minus they call this stationary state. If it's one site catalyst like enzyme, this is the lowest energy with the most stable binding species to the catalyst. There's no difference. It's good. But if it's for surface catalyst, in the energy diagram, you see the stationary or resting state is A star plus B star. But if you look at the surface under reaction condition, you cannot see A star plus B star. You see almost all A star. If you look at the two sides, it's actually A star plus an ignorable fraction of B star. So it's actually consistent with the energy span model, but you have to redefine the resting state in the energy diagram.
Omar, I had a quick question.
Yeah, go ahead.
So I can't type questions into the Q&A, I think. My question was, when you have linear free scaling and the free energies of A star and B star and C star scale with each other, how do you account for that when you use the chain rule? Because each of those are dependent on something that isn't clear to me.
Yeah, this is a good question. So first, the DRC is a mathematical partial derivative. Like, let me go back to the original one. Yeah, it's the, so when you change, for example, you change from one catalyst to another one, the energy of all species will change by some amount. But what we do is we just look at the final energy. We don't look, we look at the energy change independently, because if you change the catalyst or do some other change, energy of all these species will change. We just look into the energy change and the result of the energy change on the rate separately, one by one. So it will not affect if they are related to each other. And also you can look at the paper published by Philip Christopher on ACS catalysis. This is the only DRC paper published by their group. They actually did the thing you said. They relate the DRC analysis with the linear scalar relationship. So the final result of their paper is, in our equation, we have the summation of the DRC times the energy difference. In their method, they replace this DRC as a weighted factor of the DRCs of the species which are related together. And the energy change here is not the energy change of individual species. It's the energy change of the descriptor. So for example, this can be sigma, the combination X of carbon star times the energy change of binding energy of carbon, plus the combination of DRCs for oxygen binding energy times the energy change of oxygen binding between these two catalysts. Hope this answered your question.
All right, great, thank you.
All right, thank you, Zongtian, for an excellent talk. And with that, that brings us to the end of the talks, but there's one more item. One thing I want to bring up, if you can still use the Q&A before you head out, put in any suggestions you have about what you would like to see as the next topic for the next ATCAT session. And I think, John, you had some things you wanted to cover as well.
Yeah, I thought I wanted to start by thanking all the speakers. It's a really great day. Everything I thought went really well. And special thanks to Omar for hosting this and keeping it running on your end, and passing the screen around. So I thought that was also quite good. I'm going to remind everybody about the Google Docs. So what I'm hoping we'll figure out how to do here is have some discussion about what we might do next, what we could do differently. We'll have a little discussion on the polls. I think Omar's going to take a little bit to work out what all the responses were. But I've been watching kind of during the day, and we've had over 200 people all day long between the Zoom channel and the YouTube live channel, which is really amazing. So thanks everybody also for sticking around all day. So Omar, do you want to go through those and read them? It's a little small on my screen.
Sure. So yeah, like John was just saying, you all made it a great day. We had a peak attendance of about 299 people at a single time. So thank you very much, and hopefully you all enjoyed it. The first question was about a poster session. It seems about 81% of you would like to see an AtCat online poster session. So we're definitely going to be finding out how to best do this. Also, another question was, how often would you like to see an AtCat online session? And it seems the most popular answer, with about 47% of the votes, was monthly. And then the next most popular answer was quarterly, with about 23%. We're definitely going to be taking that into consideration and find out how we can make this happen more often. And then there was a question about early career sessions for assistant professors, young faculty, aspiring faculty, grad students, postdocs. Overwhelmingly, 88% of you said yes, there should be an early career session. And then in terms of our demographics of what best described you, about half of you were graduate students, 18% were postdocs, 12% were faculty, 11% were industry, 3% were our national lab colleagues, and 3% fell under some other category. So this, thank you for, I was impressed with that all of you voted, so thank you very much for that. This will definitely give us a lot of great information we can use to better plan the next AtCat session.
All right, so I see a couple of comments coming up via chat and Q&A. So it looks like there's some topic ideas for electrocatalysis, something data science related would be probably a good topic. Was the amount of time we did? This was 11 to 3, so that's been 4 hours since we started. That seems like a good time to me. If anybody wants to weigh in on that. And let's see if there's anything happening on the Google Doc. All right, so on the Google Doc, so we are recording this, and I think, Omar, correct me if I'm wrong, but the recording will have to get rendered after we end the meeting, and then we'll have to figure out where we're going to put it. Is that right?
Coming to my local computer will probably take a few hours to render once we're done, and then we'll figure out how to share it with everyone.
Okay, so I think our first thought is that probably we'll get it on YouTube. It's a good question that we haven't figured out if we can post it in one giant chunk or if we'll have to split it up. So it could take a day or two for us to figure all that out. But what we'll do is post in the original Google Doc the directions and link to where that is, and you'll see it on Twitter, I'm sure. So it looks like the timing is good, especially for those in Europe. I'm glad to hear that. That we moved it so that it would be pretty well aligned with you.
Yeah, I think
Go ahead, Omar.
that we didn't want to start too early for those people on the West Coast, but not too late for those in Europe and Asia, just to make sure there's an optimal time that everybody can attend.
Yeah, Raul suggested a final kind of open discussion about the main topics could be useful. Yeah, I think this is probably fair use in copyright.
Yeah, if there's anybody interested in continuing the discussion, what I can do is give you the opportunity to unmute yourself if you would like. Just let me know in the chat and I can do that.
Has anybody been to a poster session online that they thought worked pretty well? I know RSC ran one a week or two ago on Twitter, and I believe the gist of it was that you posted your poster on Twitter, which I would assume has the same issues that Ashi's worried about in terms of copyright there. And then people would reply on tweets to the students.
Yeah, I think Paul Danhauer has some suggestions on this, so I unmuted him if he wants to chime in with anything.
Paul?
Hey guys, can you hear me?
Yes.
Yeah, RSC did this, and they did it all by hashtags. So you search for a hashtag on the topic, and then you can find all the posters in that topic area. And then they were there, and then they did like a 24-hour period where posters were printed, and then people interacted, and then it closed after 24 hours. It worked very well.
So another possibility that I could imagine is similar to how the ACS Colloids division ran theirs, is they kept a centralized Google spreadsheet with links to Zoom rooms, and you would just go to the sheet and then you could click on one to enter a room. And so if there were people that had access to Zoom, they could host their own room to talk about their posters. I guess that would limit participation to people that had Zoom. Raul, did you have something you wanted to say?
Hello.
Yes, did you want to say something?
Hi.
Hi, Butena, would you like to say something?
Thank you very much for this talk.
You're welcome. Paul, are you raising your hand to say something?
No, I must have clicked on something.
When we have other sessions.
Could you say that again?
When we will have other sessions.
Oh, that's what we're trying to work out. We're trying to figure out, what kind of interest is there, how often. It sounds like monthly or quarterly is probably the time frame that is reasonable, especially given that all of us are teaching online and living at home and trying to do a bunch of other things.
Especially for first career and the beginners, PhD students on Catalyst.
Yeah, I think we'll probably try to do something again, maybe towards the end of April, early May, perhaps.
Sorry, but I heard that you will do a poster session on Twitter or something like that.
We've been brainstorming about ways that we could do that.
Okay. So thank you so much. We are going to keep searching on this.
Sure. Alexander, a poll for topics for talks or posters. If you could put in those ideas in the Google Doc that I linked to, that would be super helpful.
Okay, we will follow you on Twitter to see the news.
Super.
Thank you.
And yeah, if you have ideas on topics, you can put them in the Q&A now. I think, you know, we were talking about sharing the experience of organizing this a little bit earlier. So we're happy to share how we did it. And, you know, we're not experts on some of these topics like that I've seen on here. So it wouldn't make sense for us to personally organize it, but we're happy to help other people figure out what we did.
Okay.
Yeah, I guess one way we can try to better pull what topic to do next, in addition to a lot of the suggestions here, we have the option to send you all through Zoom a poll after the seminar is over, and we can try to build into that the different topics or suggestions for different topics that you might have. If you get that link, definitely let us know what topics you think you would want to see next.
I guess one thing that would be different about the next one, this one you already had a solicitation more or less for abstracts and a review process for selecting them. That's something we would have to work out, I think, how to get abstracts, how to review them, or if it's by invite only, or, you know, sort of exactly what you want in a symposium like this.
Omvir, you had your hand raised. Unmuted you if you wanted to say something.
Hi.
Is that Alexander?
Yes, you hear me?
Yes.
Well, just first of all, thanks a lot. It was really well organized. The time zone was it was amazing. Thank you. Secondly, I was interested in organizing something on the line for plasma catalysis. So yeah, I offer myself as a volunteer for that. I already have 3 people that could be interested. So that would be an option if that is of interest.
Okay. I think I assume there's at least 3 people that are interested in that. I think we could chat offline how we got this organized, and I think the ingredients are pretty simple. You have some talks. You find a day that everybody can give the talks and have a schedule, and then one of the keys to the success of this was a marketing strategy that Paul Dauenhauer really led in broadcasting it on Twitter. We emailed quite a lot of people. We put it on LinkedIn and had at least the PR people at CMU also put it out in some ways. So those are, I think, the main ingredients, besides having some pretty enthusiastic partners in Omar and Paul and Zach to kind of put it all together.
Okay, thanks.
All right. The recent comments from Abdul Rahman raise a sort of interesting point in my mind, which also is how do we increase the amount of industry participation? So I'm pretty excited actually to see 11%. Somebody asked in the Google Doc very early whether we would accept talks from people in industry. And I think the answer is we would love to. That would really help build, I think, a stronger kind of industry catalysis involvement. Thanks, Charlie. Thanks for your talk. That was really great. All right. Well, I think there's still a few comments coming in. Sounds like we probably, so the organizers will kind of catch up after this meeting's over and kind of review what we learned. Maybe we'll collect a couple of the topics that are in these comments and others and put them in the Google Doc and then try to figure out what a plan forward might be. I guess the next thing we might try is either a poster session or an early career session. That's what I gathered is kind of most of greatest interest from the polls. Is that your read, Omar?
Yeah, there definitely seems to be an interest in early career sessions. Maybe we can combine that with some of the topics that are in here. I think there's a lot of great suggestions for some timely topics. But I think, yeah, it sounds like maybe if we shoot for a month from now, another AdCat session with a different topic.
Okay. I think we could definitely hit a couple of these topics with an early career. And then we'll have to brainstorm a little bit on how to do a poster session. The RSC Twitter format seems okay, but it could also be interesting to try having the sort of decentralized list of Zoom rooms. So, all right. Well, I think probably we should wrap it up then and get on with our days. Hope everybody's safe where they are and having a good rest of the day, good rest of the week. Oh, can we make a Twitter account for @cat? You know, I would be stunned if that actually exists or doesn't exist.
I've looked it up.
Anybody
There's
know?
another @cat Twitter account.
There is already one?
Yep, it's about somebody's cat.
Yeah, that makes sense. Wow. I bet you there's @stray_cat too.
Yeah.
Indeed, there is. All right, we'll work on some way to do that. Seems pretty easy to just follow Paul if you can like keep up with it. All right, thanks for the comments, Aditya and also Raul. And the early career sessions, I think, could be geared either for industry or academia. We would need some help, I think, gearing it towards industry. But if there was somebody in industry that could help us do that, I don't see any reason why we couldn't. Also, Ashi, what you described is just basically how we all lecture now. At least those of us that are teaching online classes at universities that have closed are pretty much all doing exactly what you described, where the students have something open and are doing something while we do it. All right, Omar, is there a way to close the Q&A or shall we just agree that?
No, I can't. I can close the polling, but not the Q&A. We would just have to end the session.
Okay.
I think we can go ahead and do that.
All right, so I've copied those questions from Q&A into, or comments into the shared document, and just in case, I've got the chat saved as well. That should get saved automatically when you do it.
Yes.
All right, well, I think that's probably good. Let's see, Zach, did you want to add anything before we wrap up? Are you still around?
No, I think that's it, John.
All right, well, great. Thanks, everyone. It's been a great day.
Great. Everyone stay safe.